AV. Very glad to be here. I've been avidly watching Terraina over the years. IBM has been a big sponsor of Terraina because for us, this is a place to see where the Internet's going, how users are using advanced networking, and some of the problems and challenges we might have going forward. This is actually the most important slide of the whole deck. That's because at last count, there are 15 Mike Nelsons who work for IBM. So if you don't have my email address, you will be unable to find me. So write it down. mrn@us.ibm.com. I've got a somewhat unusual background. My PhD is actually in geophysics. So I'm actually out of the user community. I'm one of the people who puts the stress on the networks and one of the people who tries to find new ways to make more bits to clog the pipes. After I finished my PhD, I went to Washington, D.C. on a one-year fellowship for people who want to help congressmen and senators understand science and technology. Turned out I got Potomac fever. I hope that's not terminal. But I ended up working for Senator Gore, and I was his science advisor for 5 years when he was a senator. The reason Senator Gore has a reputation for giving very boring speeches about science and tech is because he hired an MIT PhD to write his speeches for him. My main accomplishment when I was working on the Hill was to help Senator Gore write legislation that allowed the commercialization of the Internet. We think that was a good thing. After 5 years on the Hill, I went to the White House because Senator Gore got a promotion to vice president, and I spent 4 years there. I left just before Monica Lewinsky got in the headlines. This was a good career move. I then spent a year and a half at the FCC trying to help them not regulate the Internet, and finally ended up at IBM, where for the last 8 years I've been working on Internet standards. I manage a team that includes Brian Carpenter, David Martin, several people that you know, who have been very involved in grid standards and on IETF standards. But a large part of my job is working with external groups like Terraina, like Internet2, to help understand what is actually happening on the Internet and what the future is. I also spend a lot of my time on Internet policy issues. I have this unique experience where I spent half my life in the policy world and half my life in the technology world. And so I try to help the two worlds communicate together. What I'm going to do today is share with you some of the things I learned in my time on Capitol Hill and at the White House, and share with you some of the things I see coming as the Internet develops. I'm not going to focus on the bits and the bytes and the pipes. I'm going to focus on what's happening on top of the Internet, the applications that are driving some of the traffic. So first, let me share with you some of the most important things I learned in Washington. I actually have a talk called 50 Things I Learned in Washington. It's about an hour and a half speech. Summarizes everything I learned in 10 years. But let me share with you just a few. The first, most important, is always have a good bumper sticker. You always have to be able to summarize your key points in 8 words or less. So I'm going to give you some bumper stickers today about what the future of the Internet has in store. The second point is that if you really want to make a point effectively in Washington or in the media or in the boardroom, you need at least 2 factoids. Easy to remember, very convincing statistics that help make your point. Preferably true ones. Some of you may remember that in 1996, one of the most powerful factoids ever unleashed in the Internet community was unleashed by the head of UUNet, and that was traffic on the Internet is doubling every 3 months. I think you may remember that factoid. It was actually true for 6 months. People kept repeating it for 5 years. As near as I can tell, about $100 billion was invested because people believed that the Internet traffic was going to increase by a factor of 2 every 3 months, factor of 10 every year for eternity. Another lesson that I learned, one of the 50 things I learned, is that you have to look beyond the headlines. And so I hope today to go beyond the headlines about the Internet, look at what's really happening, what stories are not being reported in the mainstream media. So let's start. The first headline has to do with bandwidth. We've seen the headlines about the Internet 2 world land speed record. Over the last 6 years, it's been a very impressive progression as we've gone from 750 megabits per second to now over 7 gigabits per second in the last announcement about 2 months ago at the Internet 2 meeting. That's a very impressive number, very impressive growth, factor of 10 in 6 years. And that's made the headlines. But more important than that, actually, is the even more impressive growth in what's happening at the last mile. We've seen this as fiber gets rolled out to homes in the U.S. and even more rapidly in Hong Kong and in places like Singapore. We now have people buying 50 and even 100 megabit per second connections for less than $50. That's profoundly changing the traffic load that we see on the backbone of the net. In many cases, this is not asymmetric, this is symmetric traffic. So people are broadcasting out to the net at megabits per second. Second headline is just in the last few months, we've seen a whole bunch of very exciting stories about the old media companies discovering the Internet. You can now get Desperate Housewives online. This is progress. So Warner Brothers, Fox, a number of companies have decided that they're not going to be Napsterized. They're not going to let somebody else steal their content and put it out online. They're going to do it themselves. The story that isn't making as much news is that people have already done this. There's already a huge amount of traffic out there, a bunch of video that's off the commercial networks. But more importantly, there's a huge amount of amateur video, material that people are making on their own, often for a few $100, and broadcasting to the world using BitTorrent in particular. One of the headlines that we haven't seen very much is just how much traffic on the net today is due to BitTorrent. Some of this is Linux kernels being distributed by geeks, but most of it is video. Much of it just amateur video people are producing on their own. 2 years ago, 30% of all the traffic, according to Cache Logic, was BitTorrent. They just reported that about half of all the traffic is due to BitTorrent, a peer-to-peer service that allows you to dump huge amounts of traffic and distribute video very easily across the net. In some countries, 70%, two-thirds of the traffic on the net is due to BitTorrent. And as I said, this is due in part to people making their own stories. There's an incredible community of people out there who are so addicted to Star Trek. They've watched every episode ever broadcast 15 times, and they're now making their own episodes, using the characters who are out there. Sometimes these are quite sophisticated. These are people using film students who've gotten bored, creating their own content, being distributed across the net. You can now make videos of your gaming experience. So if you had so much fun in a particular game with your friends, you can record that and you can share the experience over and over and over again. And of course, webcams are everywhere. You can go, at last count, there's a site called webcammania.com. Over 10,000 different webcams on 24 hours a day. City centers, the view from cruise ships in the Caribbean, you name it, there's somebody showing something somewhere. And again, this is adding to the traffic on the net. Third point, another headline. We've all heard about the grid. We've heard about TeraGrid, EGG, demonstrating grids that are able to deliver more than 10 teraops per second, as powerful as many of the largest supercomputers. That's made the headlines, a lot of interesting stories there, lots of money being spent to build these grid demonstration projects. But the other news that isn't getting as much attention is what's happening when we tie together thousands of machines. These grid projects are dozens of machines, very powerful machines connected with 10 gigabit or 40 gigabit per second networks. But even more impressive is what's happening when thousands of servers and hundreds of thousands of PCs are connected. Most of you are familiar with Akamai. But most of you may not know that 15% of all the internet traffic in the US and in most countries comes out of an Akamai server. People are not going to the CNN.com server, they're going to Akamai to get the bits that they want from CNN.com. That really means that Akamai has built the world's largest storage grid. Thousands of Akamai servers scattered around the planet, serving up content to millions of people every day. And again, this isn't making the headlines, because it just sort of slowly happened over the last 5 years as Akamai signed contracts with more than 1,000 of the major web content producers and distributed their content across their server farms across the net. Even more impressive, perhaps, is what's happening with all the PC-based grids out there. All of us are familiar with SETI at Home, which was the pioneer in this area. They've harvested hundreds of millions of dollars of spare computing cycles to help find little green men. So far, no news on that front. But they were just the pioneers. There are now more than 100 major projects that are doing everything from fighting AIDS to curing cancer to breaking codes to finding the world's largest prime number. As I sit here, my computer is being used to cure AIDS as part of the World Community Grid, which is an effort that IBM initiated to donate cycles to various research projects as a charitable effort. We've got over 100,000 donors who have donated cycles on over 170,000 machines. For less than $500,000, we are generating more than $100 million in computing power. And there are dozens of different projects. If you go to www.distributedcomputing.info, you can sign up for any one of these projects. You can sign up for a different project every week for the next 2 years. And by then, there'll be another 100 projects that you can sign up for. This is, again, an example of how much computing power is out there in the net that we could be harvesting for all sorts of purposes, and which today are being harvested. Another example of how the net is becoming the grid is what's happening with the hackers. And you've got thousands of hackers who are today infecting thousands, even millions of machines, turning them into zombies and using them for all sorts of reasons, all sorts of nefarious purposes. And I think our next speaker, when he arrives, will talk about that in more detail. There's hackers who, before breakfast, will take over 2,000 PCs and start spamming the world using the computing power in those machines and generating a pretty good income simply by serving up pornographic ads to grandmothers across the world. Headline number 4, and we're going to hear more about this at this meeting. Scientists and engineers are using the access grid, using VRVS to collaborate more effectively on research projects. Very exciting, very important. But again, not the real story. The big story is that millions of people are using the net to collaborate together in games, to do very sophisticated collaboration, using voice over IP to interact with each other in virtual spaces, often not 5 people or 10 people, but 100 people at a time, all working together or against each other in various games. At last count, the gaming industry, this virtual world that's been created out there with hundreds of different multiplayer games, are producing economic results equivalent to the GDP of Belgium. This virtual world out there is taking up so much time, so many man-hours, and producing so much income that we now have an industry that's producing billions of dollars. There was an exceptionally useful article that just came out in Business Week last week. This is the May 1st issue of Business Week. It's got a cover story entitled Virtual World, Real Money. And this woman, this virtual woman, is Asha Chung, a cyberspace real estate developer. There's a real person behind this avatar. But this woman in China is making $200,000 a year by creating virtual real estate in one particular game. By building houses, developing shopping malls that other players in this game will use. She charges a small virtual fee, which actually can be turned into real money. So again, big business out there. This isn't something that just a few freaks are doing. This is something that tens of millions of people around the world do every few days at least. As we sit here today in South Korea, 400,000 people are playing the game Legacy right now, interacting with each other, trying to storm the castle or fight off another army. And these other games that are documented in this Business Week article are even larger. And you can do everything from take over a galaxy to build a virtual home. Fifth point. This is the headline on entertainment. We just saw that News Corp bought MySpace, which is a social networking site, for $580 million. That was an eye-catching sum, so it made the headlines. How many of you have used MySpace? How many of you have teenagers who use MySpace? MySpace is a site that allows you and your friends to interact together, to share music, to share ideas, or to just chat. And the headline here is that the Internet isn't just a medium anymore. It's not just a network for moving bits and bytes back and forth. It is a place. And it is a place that 20 million MySpace users go to every day. And most of them are spending 20 minutes or more interacting with their friends. This is a very immersive experience that goes way beyond chat. They can talk to each other, they can share music, they can share images, they can surf the web together. It's much bigger than just sending email. This is something that is fundamentally different, and it's different because of the way these kids think about the net. They're not just using it to move bits. They're thinking about it as a space, a place where they go and hang out. Similar things are happening in China. At last count, we had 111 million Chinese users of the Internet. Pretty soon there will be more Chinese users of the Internet than American users of the Internet, and China will be the largest Internet country in the world. What's interesting about many of the Chinese teenagers who are using the net is that they don't have email addresses. They don't think of the net as a place to send mail back and forth. Perhaps it's because they're worried their email will be censored or used against them. But actually, the reason they're doing, by the way they're using the net is just to chat. They just go on, they chat with their friends, and then they're off. There's no presence left. Another headline is about spam. And we've all experienced spam. We've seen the headlines. And the usual story is spam is out of control. And there is way too much spam. I've got way too much in my inbox. But the good news here, there is a good news headline, and that is that the vast majority of spam is now being blocked. It's either being blocked on the sending end or being blocked at the receiving end by your corporate firewall, by your own personal filters. So we are making progress here. We have a long way to go, but we are making progress. If we can do more on authentication, I think that clearly will help. And that leads to the seventh headline, which is about authentication. We've heard about various efforts by the private sector, Microsoft's Passport, Liberty Alliance. In many cases, they've been developing authentication technologies, badly needed authentication technologies, that are based on their own proprietary systems. And that's one reason they haven't become universal. They haven't really spread. They haven't been implemented in all products everywhere. Because of the marketing budgets behind Microsoft, we've heard a lot about Passport and now info cards. But we haven't heard the other news. And that is at the same time there's a parallel effort in the open source community using open standards like SAML to build truly universal authentication. Develop federated identity management systems like Shibboleth, which you'll hear more about from Ken Klingenstein. These systems are going to, I think, solve a lot of the problems we have today on the net. They're going to help us alleviate the spam problem. They're certainly going to help cut down on cyber fraud and phishing. If you have universal authentication, you have a way of knowing whether that email that says it's from PayPal really came from PayPal, or whether that email from Nigeria really came from somebody in Nigeria. The latest issue of MIT Technology Review has an excellent article on 10 top technologies to watch across the fields of biotech, infotech, and the like. Universal authentication is one of those 10 technologies. So this is an area to be watching. When we get this, I think we'll be able to move more quickly in a number of very exciting applications. And now let me get to my last headline. This is one I'm going to devote a lot of time to because I spend a lot of time in the policy world. And this is the headline about Internet governance. How many of you have been following the Internet governance debate? This is kind of scary stuff. The headline that I've seen more often than not is United Nations wants to control the net. And for the last 3 years, there have been a number of UN meetings, 2 meetings of the World Summit on Information Society, which was meant to focus on how the Internet can move into corners of the world that it hasn't yet spread to, and how the net can serve more people more effectively. Unfortunately, many of the meetings deteriorated into debates about who controls the Internet and attempts by certain governments to exert more control on the net. And that the first focus was on DNS, the domain name system, and ICANN, and whether the U.S. has too much control over that. Fortunately, one of the good results of this whole process of the World Summit on Information Society was that governments came to realize that it wasn't all about ICANN, that ICANN somehow was not in control of the net. I think most of us understand that ICANN probably makes somewhere between 2 and 5% of the important decisions that shape the net. I think the people in this room probably make at least have at least that large an impact on how the net will develop. But for whatever reason, governments around the world got very excited about whether there was going to be a .xxx domain name or not, and whether ICANN was incorporated in was a nonprofit organization incorporated in California or incorporated in Switzerland. But throughout this whole debate, there was a clear message, and that was that governments need to have more control over the net. And while we were all debating ICANN and paying attention to these summits that were held in Geneva and in Tunis, something else important was happening, and that was that governments were trying to exert their control. Governments have come to realize that the Internet is fundamental. It's a critical information infrastructure for entertainment, for e-government, for political speech, and as a result, many governments are trying now to regulate it. And while we were focused on Tunis, there have actually been dozens of efforts around the world to impose new regulatory controls over the Internet. Many of you are probably familiar with what's going on in your country, but the fact is this is a trend everywhere, from the U.S. Federal Communications Commission to China to Brussels and the European Commission. This slide is one I borrowed from Tony Rutkowski. He gave a talk about 2 months ago at the ITU in Geneva, and he tried to document all the different organizations, all the different agencies that are trying to we're putting forth proposals that will put new constraints on the Internet. You don't need to read all of these different bubbles, but it includes many of the usual suspects, like the Federal Communications Commission in the U.S. and the European Commission. But it also includes justice ministries, it includes UN agencies. There's a lot going on right now. In my spare time, I'm Vice President for Policy of the Internet Society. I hope most of you are members. We have been helping governments understand how the net really works so that they do not do stupid things based on old models and old ideas of networks. But we have an uphill battle. Lots of different countries, many different agencies, all getting involved. As scary as this slide is, I think this slide is even scarier. This is another slide from Tony Rutkowski, which lists all the different reasons that governments are trying to control the net. Clearly, there's a lot of concern about cybercrime and security. There's a lot of concern about competition and ensuring that there's a competitive marketplace, that new entrants can enter the market. There's a lot of concern about universal service. How do you ensure that all corners of your country are served by the Internet and new Internet services? Emergency services, e-government, the list is a very long one. And we need to be paying attention here, because in too many cases, what's happening is the lawyers and the politicians and the policymakers are just taking out the old rules that were developed for the telephone or for the radio or for TV and imposing it on the internet. Another area where there's quite a bit of interest is in the area of consumer protection, ensuring that the disabled community can get access to the net, ensuring that that private personal information about your use of the net is properly protected. And this leads me to lesson number 17 from my list of 50 things I learned in Washington. There is nothing more dangerous than an old model applied to a new medium. And that's what we are seeing time and time again. We're seeing old broadcast rules applied to the net. We're seeing rules about telephony applied to the net. This is because of a fundamental misunderstanding of how the net really works. And everyone in this room can get involved in changing that fundamental misunderstanding. When you ask governments how things should be governed, they often look to old models. This is postal governance. This is how the mail system was run for years. You had hundreds of governments with monopoly post offices, and they served the people, and when they needed to coordinate, they went to the Universal Postal Union in Geneva. Same thing for phone governance. And again, this is the model that is in the head of many senior government officials. You had hundreds of governments, many of them running or owning a monopoly phone company, and at the bottom of the pyramid you had subscribers. They were not called customers because they couldn't customize their service. They were not called users. They were called subscribers because, like a magazine subscriber, you could take it or you could leave it. You didn't have a choice over how much you paid or what service you got, or in the U.S. you didn't even have a choice over what color your telephone was until the 60s. But the point was, it was a top-down system. And when there was a need for coordination, governments would go to the ITU. Very simple, one place, one stop, and that's how they worked the system. Our challenge is to change that paradigm. All of the talk about internet governance over the last 3 years has focused on taking this kind of top-down structure, government-led structure, and imposing it on the internet. Our challenge is to show that that's not how it should work. In that system, governments have the lead. Governments tell the phone companies what to do, they tell the ITU what to do, the ITU coordinates, tells the phone companies what to do, and that, in the end, is what and the customers then take the result. With the net, we've turned the whole process on its head. With the net, millions of internet users are in control because we have a competitive marketplace. Millions of internet users are telling, through their choices, through the decisions they make every day, they determine what services are provided by ISPs, by hardware and software providers like IBM. They're the ones forcing the agenda. Their decisions, in turn, shape government policy. Governments have a role. Governments do enforce all sorts of laws on consumer protection, on competition, but governments are not in charge. And when there is need for international cooperation, they don't go to the ITU. Instead, there are literally dozens of different important groups that are making decisions about how the net evolves, all driven by the millions of users who are making choices. These different international bodies include ICANN, include the Internet Engineering Task Force, the W3C, which makes web standards, ad hoc consortia of companies that might team together to develop new technologies. In some cases, it is government institutions. There are very important roles for government in cybercrime and trade issues. But the point is, there isn't one particular place to go. And this has made governments very uncomfortable. It's confused them, I think. So it's been difficult for them to understand this new model. But slowly, they are learning, and with the help of people in the technical community, we're explaining where the different decisions are and how they're being made. In this world, individuals have the power. Individuals tell the vendors what they need, and the dollars and euros they spend determine which products succeed or fail. The vendors put pressure on international organizations and governments to get the right policies so that the individual will be served properly. Let me spend some time now on some of the things that I'm worried about as Vice President for Policy of the Internet Society. These are the issues that aren't making the headlines, but which could have a profound effect on the development of the Internet and could really limit some of the most exciting new applications that we're seeing come out of the academic community, come out of the hacker community, come out of the gaming community, come out of the entertainment industry. The first one is coming out of Brussels, and that is the European Commission's Television Without Frontiers Directive. How many of you have paid any attention at all to this? That's good. 3 is better than none.
Can I hide under the desk?
The problem with this directive is its name. I told you about bumper stickers. Well, by calling it the Television Without Frontiers Directive, the Commission guaranteed that most Internet people would decide they didn't need to worry about it. But the fact is, it's all about the Internet. It's about controlling the content and the type of information and entertainment that's delivered over the Internet as television migrates into cyberspace. And some of the things that are proposed are written in language that is so vague that it could definitely limit freedom of speech, could definitely limit academic broadcasting and lectures. It could really impose 50 years of broadcast regulation on the Internet. Even more dangerous, and I would say even more insidious, is something coming from the World Intellectual Property Organization. There's a new treaty called, a proposed treaty, called the Treaty on Protection of Broadcasting Organizations. How many of you have paid any attention to this? Okay, 1 is better than none. This proposal, again, sounds like it's all about broadcasting. And when you talk to people in the community of intellectual property lawyers who are negotiating this treaty, they will start by focusing on over-the-air television and cable television. But they will mention that there is this section on webcasting. If this treaty is passed in its present form, it would create an entirely new intellectual property right. This isn't a copyright. It isn't an intellectual property right for the person who creates the content. It is an intellectual property right for the webcaster. So if I'm a webcaster and I take your content and blast it out to the world, I now have a 50-year right to control how those bits are used. This is an intellectual property lawyer's dream come true. Since we're looking at a world where there's going to be 50 to 100 times more content, if this treaty is passed, we now have 50 to 100 times more contracts and deals that need to be done to determine who has the rights to a particular set of bits that are webcast over the net. Luckily, last week in Geneva, the WIPO had a high-level conference to decide whether to go to the next step to negotiate this new right that would fundamentally change the economics of the net. This isn't a minor thing. Imagine all the problems we've had with copyright over the last 5 years. All the problems with Napster, all the lawsuits, all the challenges to universities who have had to clamp down on their students who were illegally file sharing. If this new right is put in place, not only will Hollywood and the movie producers and the music producers be enforcing their copyright, we will now have all of these companies that are in the webcasting business also trying to protect and control how their content is being distributed. This treaty only makes sense. The only reason you would ever want this treaty is if you are trying to build a pay-per-view world where every bit has to be paid for every time you see it, and where there are digital rights management systems in place to make sure that you pay every time you see something. It's where fair use goes out the window. This is a very serious effort. It's one that has a lot of very powerful companies behind it, and it's one that has not been in the headlines. So I'd ask you to pay attention to this, or make sure somebody in your organization is. Third issue that's gotten a lot of attention in the U.S. and has actually made some headlines is the effort by the Federal Communications Commission to regulate voice over IP. Here we have a situation where 50 years of telephone regulation are now being imposed on voice over IP, because voice over IP looks like telephony. I think most of you know that voice over IP is a lot more powerful, a lot more versatile, a lot more interesting than plain old point-to-point telephony. But because there are services that are competing against phone companies, the FCC has seen fit to impose rules on wiretapping and on emergency services, so that voice over IP providers now have to pay money to the existing phone companies to make sure that you can make an emergency phone call from their systems. And again, this is creeping regulation of the net. It's new ways to impose old rules on this new medium that could close down some very exciting opportunities. It may make sense to impose some of these rules on voice over IP services that are meant to be replacements for the phone. But voice over IP is being used for gaming, it's being used for video conferencing. There's a whole range of places where it's being used where these old rules won't make sense, and yet they are being imposed. Here in the fourth point has to do with wiretapping and data retention. Here in Europe, the European Commission, led by the UK, has been imposing rules on the collection of data on who is sending email to whom, and requiring that ISPs keep at least 6 months of data so that terrorists and pedophiles and other criminals can be tracked. Again, this is logical if you're thinking in terms of the old world of telephony, where phone companies routinely track who's calling whom. It may not make sense in the world of MySpace and mega conferences where thousands of people are interacting with each other, where there's 101 ways to communicate without using email. And yet, hundreds of millions of dollars will be spent imposing these rules or meeting the demands of these rules. And the technical community has not been involved enough in making sure these rules are done in an effective way that protects innovation as well as national security. Fifth item on my list, the fifth thing that keeps me awake at night. You can see I don't get enough sleep. And that is the International Telecommunications Union's effort to create new standards for the Internet. They have something called the Next Generation Networks Initiative. It's very hard to understand exactly what this is because several different versions of it have been proposed. Some of it's written in bureaucratic language that's a little bit vague. But the bottom line is that you have people going around the world saying that the Internet is broken. We need new standards to fix the Internet. And some of the proposals that are being on the table would fix the Internet in ways that would be very destructive to the openness and freedom and innovation we see today. It would actually create islands, walled gardens on the net as an excuse to ensure, using the excuse of security and the need for better authentication. In some cases, it would give the phone companies much better tools to exclude services and new entrants from the marketplace. Very scary stuff when you look at the details. Good news is that in many cases they are trying to use existing standards from the IETF and the W3C and OASIS. The bad news is they're putting them together in ways that could really restrict what's happening. I went to a NGN meeting at the ITU 2 months ago. Unfortunately, they scheduled it at exactly the same time as the Internet Engineering Task Force meeting was being held. So there were a lot of bellheads in the room and not a lot of netheads in the room. And I think as a result, they're moving in a direction that could really, really change the architecture of the net if enough people adopt their standards and support their initiative. Another thing that has been an increasing worry in the U.S. and in some countries is the increasing consolidation in the telephone and ISP industry. as we've gone from dial-up ISP service to broadband, we've seen consolidation. We've seen consumers being given fewer choices if they want to stay at the leading edge. And as a result, there's been growing concern that the Internet will cease to be a competitive marketplace. This worry has been made worse by the fact that a number of CEOs of major telephone companies in the U.S. have said things like, well, I don't know why we should let everybody get to every website. These are our networks. We control these networks. And the proposal has been made that they should start charging Google and Yahoo and content providers for access to the net, or better access to the net. With the development of deep packet inspection techniques that allow an ISP to actually filter out different types of content, it becomes possible for an ISP to restrict what kind of Internet experience you have and what websites you go to, and as a result allows them to give preferential treatment to their own sites or to their partner sites. And so there's a growing debate in the U.S. about what is called net neutrality, and whether there's a need for government to step in and guarantee that the net stays open, that the Internet really does allow you to access everything that's connected to it. And so I'm being signaled.
No, I'm being signaled.
Okay. Does that mean I'm running out of time, or does it mean we don't have a speaker?
It means you have plenty of time.
I have plenty of time, okay.
Unless Rob is sitting somewhere in the auditorium and we haven't spotted him.
Okay.
No, right.
Okay, anyway, there's this huge debate going on. There are a few other countries where we're seeing similar debates. The fantasy that some phone companies have is that they're going to be able to impose on the Internet the business model that the cable companies have used so successfully in the television industry. In a typical cable television system, you have about 750 megahertz of capacity, and as a result, you have a good excuse to control what channels are put over your network and to charge the content providers for access to your net. That's the kind of business model that a lot of the telcos now would like to impose on the Internet, where they can start auctioning off rights to use their network. The result of all this debate is that we have proposals in the U.S. Congress that would impose net neutrality requirements, that would actually ensure that phone companies do provide service to everything and connection to everything, and not favor one company over another. The problem with this, of course, is that it's a very bad idea to have congressmen designing networks. And all of the proposals that have been put forward so far would do a lot of damage to some of the very exciting applications that are coming out of this community and out of the startup ventures in the U.S. One of the simple-minded bumper stickers that you hear in Washington is, net neutrality means every bit is treated alike. That sounds really good to a 23-year-old congressional staffer. Yeah. What could be better than equality for bits? I think all of you understand why that's a really dangerous thing. We have a whole range of applications that depend on certain bits being treated differently, being given priority. Akamai treats bits differently. Some of the emergency services solutions that have been proposed treat bits differently. Some of the grid applications treat bits differently. And a simple-minded net neutrality regulation that says all bits the same would be a very dangerous thing, even though the intention is good, which is creating an open net. So the answer here, I think, isn't to try to write regulations that somehow enforce net neutrality. The answer, I think, here is network choice, making sure that every individual, every company has many different Internet providers to choose from, because in that kind of world, the users will be in charge. We'll have the flipped pyramid, where the users can demand net neutrality from the ISPs, where the users can get the services they want, and where they can be sure that they can get to every corner of the net without a problem. As we go forward, in the next 2 or 3 years, we're making an incredible number of very important decisions about the net. technical choices. These are standards choices, and they are market choices that will determine what the net looks like in the year 2011, 5 years from now. These are the choices that really define the net, and they're being made in some very obscure places. The IETF, W3C, ICANN, Unicode, lots of places that policymakers and reporters don't attend and don't even know about. I would argue that right now we are at a more critical point in the development of the net than at least, probably than we've ever been. You might be able to argue that the early 90s, when we were having the browser wars and we were determining whether there would be one standard for the web or not, were almost as critical. But I would think right now, because there are so many different choices that we're making about authentication, about privacy protection, about digital rights management, about voice over IP, about grid in particular, about web services. All these different things are happening right now, and the choices we make will determine whether the net continues to be this platform for innovation or whether it starts to close down, and whether the people behind NGN or similar efforts succeed in restricting innovation and new services. The good news for the policymakers is that if we do some of the things right in the technology world, we will solve some of their most difficult policy problems, whether it's privacy, intellectual property theft, pornography, security, or pricing. If we get the technology choices right, they won't have to worry about regulating solutions. If we get the technology choices right, we won't have to worry about net neutrality because it'll just happen. But we have to get those technology choices right, and we have to understand the impacts of some of the choices we're making. And that's something I spend a lot of my time doing at the Internet Society, working with people who try to live in both worlds so we can understand the big impacts of some esoteric technical decision. This community has an incredibly important role to play in this whole debate. In many of your countries, you're looked to for advice. You provide the unbiased technical advice on how the Internet works and how a particular policy decision might affect the growth of the net and how it might restrict some of the most exciting new applications. You're also a canary in the coal mine. You're a pioneer. You're out here building networks that are operating at a gigabit per second. You're running into some of the new challenges and learning to cope with them. One reason I've been going to Internet 2 meetings since their beginning in 1996 is because I've seen there how campuses deal with problems like Napster and piracy, issues like privacy and security. Because they're half a generation or a generation ahead of the commercial sector, Internet 2 and your networks are running into some very thorny problems and trying to find solutions. And I think what you do in that area will be trend-setting and help us find ways out of these tough problems. And you can test out new technologies, new standards. Clearly, this community has fostered the growth of open source and open standards-based solutions, and that's been a very, very good thing. So we have to get out there and deliver some clear messages to policymakers, and also to the general public, and particularly to the press. Lesson number 24 that I learned in Washington is that if you want to deliver a message to a senator or a congressman or a cabinet minister or a president, it's often much more effective to deliver that message through the Washington Post or the Wall Street Journal. Since I joined IBM, I've also discovered that it's also often more effective to get a message to the CEO through the media than it is by sending him an email. We refer to that as working from the outside in. Clearly, if customers and reporters start asking questions, issues start getting addressed. But we have to make our messages quite simple. And I've been to enough technical conferences to know that, and I went to MIT, so I know that engineers and scientists believe that more data is better. Isn't that why we all use 6-point type in our PowerPoint presentations? So we have these presentations that dump a huge amount of data on people. And as a result, the message sometimes does not get through. So we have to restrict our messages, get very clear bumper stickers, and first of all, deliver the message that the Internet is just starting a critical third phase. There's something fundamentally different going on now. And as a result, we have to think differently. The first phase of the net was very simple. It was mostly point-to-point. For 20 years, you used the net to log on to a remote machine, to do an FTP, or to send email. One-to-one, that's what the net was about. And then the web was created, and the second phase started. In addition to communication, the web became a content distribution medium, a broadcast medium, a one-to-many medium. Profound difference, huge increase in the amount of bits being delivered, new business models, new opportunities. And now we're at the third phase, and this is the many-to-many phase, when millions of people are interacting with thousands of machines all working together, whether it's Akamai or the grid or web services. Even a congressman can understand that one-to-many is different than many-to-many. And if we deliver that message and make it clear that right now we are on the cusp of something as big as the web, maybe people will reconsider the old assumptions. Maybe they will stop trying to impose the old models on this new medium. The other big reason, of course, that we're seeing this profound change is because we're going from megabits to gigabits. We're going from copper to fiber. And we're going from wired to wireless in many cases, unleashing a whole new set of applications. But we have to get the message across. It's not business as usual. This isn't just simple extrapolation. There's a fundamental paradigm shift going on. As the network becomes more than just a communication platform, it becomes a computing platform with storage and computing power built in. So, the other message we have to deliver clearly and effectively is that this is a global medium that does not work very well if you impose 100 different national regulations on it. And that we have to look first to technology solutions to some of the policy problems that are out there. Problems like privacy, security, intellectual property theft, those are very big and important policy issues. There are national security issues. There are concerns about the safety of children. But we have to look first to technology choices, technology solutions that will work around the world and which can be implemented in a year or two, unlike regulation and international treaty that can take 5, 10, even 15 years to implement. So I hope you'll join with me in helping implement, helping convey these messages. I hope you'll work with the Internet Society and some of the other organizations that are trying to educate the policymakers and push back against Internet governance and some of the other efforts, misguided efforts, that would fundamentally change the network that's been so successful over the last 20 years. And with that, I'm happy to take any questions or turn it over to our next speaker who isn't here yet.
Well, a final check that Rob isn't here. I haven't spotted him. No. Okay.
Perhaps he was kidnapped by the hackers.
Well, I'm sure they'd love to. I'm sure he would also want me to pass on his apologies. I've been checking the airline timetables, and I see there's at least one flight that's 3 hours late coming into Catania. So I fear he may be on that. If he does make it, we will try our best to fit him in later on in the day, or at some point in the conference. So keep an eye on the schedule out in reception area. In the meantime, that means we have plenty of time for questions and discussion for Mike. So
I hope I said something provocative enough to get a question.
Do we have? Yes, we have microphones, so if you could wait till the microphone arrives. I'm sorry, it's a bit dark up there, so if I should recognise you and I don't, apologies. There's one right on the aisle just there, and then I've spotted one just in front. So there was a hand up just in front of the exit. Yes.
Oh. Who's first?
I can,
Oh, okay.
I go first. James Farnhill from JISC. I'm currently running an e-infrastructure program where we're looking at how we actually get researchers to collaborate online. I was really interested in what your comments about the gaming industry and how successful that's been. I mean, I come from a gaming background myself. I'm obviously sort of kept up to speed with things like syndicates on World of Warcraft, etc. What, in your view, how do we get researchers actually taking those lessons and using them so they can actually collaborate online? It's fine actually having the technology there to be able to do it. How do we then get the community to sort of take that technology up? The gaming community is quite a technical one. It tends to be people from a fairly technical background. They're fairly fluid. They like using things like IRC, etc. How do we sort of spread that out perhaps to social sciences people, to people who don't necessarily have that deep technical background?
Well, the good news is it's starting to happen, in part because we have all these brilliant college students who have been gaming for 5 or 10 years entering the workforce now. And so they're familiar with these tools. They just want to know why they can't use them in work as well as in play. The other good news is that some of these technologies are open source, open standards based, and so they can actually be plugged into new applications. The bad news is that many of the marketing executives and the CEOs who make decisions about whether to develop products in this area are 45, 55, 65 years old, and gaming is something teenagers do. They don't really get it. They don't play games for hours every week. And so they don't make the connection. They don't see how some of the same technologies using in these virtual worlds could be used for collaboration among their employees. And so there's some education that has to go on. At IBM, about 6 years ago, when the internet was first becoming really mainstream, we had a reverse mentor program where about 50 of the top executives were assigned somebody who was a technical person who was under the age of 30. And this mentor was supposed to help the executive understand what was happening on the web. And there was an hour assigned every week where this mentor, this reverse mentor, would come in and say, "Hey boss, look what I found," and just kind of show them, play with the stuff, so that they could see how this technology could change things, both inside the company and in the marketplace. But it's two worlds, and they're very disparate worlds, and it is going to take some time. But I'm hopeful. At IBM, gaming is the driver. I mean, games are forcing radical changes in the way we design our chips. They certainly are influencing the human-machine interfaces that we develop. And it's partly because there's so much competition right now in the gaming industry that there's a real chance for innovation. But the biggest barriers are cultural. There's just a tendency to say, well, if the gamers are doing it, that's not real IT. That's not corporate IT. The academic community may be the place where this happens first, where the two worlds can come together. Because
so you're really sort of seeing this kind of push from underneath to actually
it's
grassroots.
I think we're going to see more and more of these open source things just kind of take over, and suddenly people will be using virtual worlds to build virtual shopping malls, and then somebody will have the bright idea that they could do the same thing for a real shopping mall. And engineers and finance people and shop owners could be interacting together to play with a virtual mall that could be the blueprint for a real one. I mean, there's some easy transitions that you could see happening, but we do have to make them more bulletproof. We have to make them ready for prime time, and they have to be easier to use than some of the tools that are out there now. But
absolutely. Yeah. Thank you very much.
Any thought you have on how to bring the worlds together, I'd appreciate that. Back here?
Yeah, good morning, Mike. Steve Wolf from Cisco.
Oh, okay.
I think you have correctly identified that the Internet is beginning to deliver on its inherently egalitarian nature with the rise of peer-to-peer applications. And I think you will also recognize that I'm not an apologist for the phone companies. Yet in the context of net neutrality and in the context of the implicit necessity for control at the edges, I would be interested in your views on what the appropriate business model for a telephone company might be.
I feel like turning off the microphones now. Let me start by saying, first of all, that 8 years ago when I left the FCC, and I had many different job offers, and I chose to work for IBM and not one of the phone companies. I think the phone companies have an incredibly difficult transition to make. And I think many of the monopoly phone companies that are enjoying profits made possible by charging $1 per minute for international phone calls are discovering that that doesn't work anymore. They do have a huge number of assets and benefits. They have a very talented technical workforce. They have long-term relationships with customers. In many countries, they have a lot of trust built up. And they often have the rights of way that allow them to get through the last mile into the home. And they just have to figure out how to use that effectively. I do think that most of them are going to be in the conduit business, and they're going to have to embrace the idea that more content providers providing more bits, and that includes homeowners and individuals and kids pumping bits upstream out of the home, as well as Yahoo and Google and gaming companies pumping bits into the home. Unfortunately, we have too many of them still thinking that they can control the networks and that they can replicate the cable television model, and I don't think in the long term that's going to work. I don't know if I've really answered your question, because I do not. If I knew the best business model for the telecom companies, I probably would not be up here talking about the Internet. I would be consulting with the phone companies. But there are companies that do get it. We're working very closely with a company in India. Bharti is the second largest phone company in India now. It's phenomenal growth, and one of the things they've done is they've outsourced many of their core functions. Billing, a lot of the management of the network is being done by other companies, and they're really not in the business of controlling and owning a network. They're in the business of providing service and bringing together all types of service providers to do the job of providing the service that their customers want. And so that would be one place I would look as a model. I would not look to the monopoly phone companies who are still trying to use government regulation in their country to protect their little monopoly and to continue to serve the wealthiest 2 or 3% of the population and charge outrageous prices. Right here in the middle.
Alex Reid, Arnet, Australia. Mike, you dismissed spam as saying we're pretty well on top of it. I don't see that. It seems to me that spam is increasing more rapidly than our ability to cope with it. Even for tech-savvy people, having struggled with spam, but I'm more concerned about the men in the street. And many of them are having a real struggle, and some are saying, I just can't cope, so I'm not going to use the internet anymore. They're the kind of people that the legislators are listening to. Where is the solution to spam? You seem to be optimistic. Where's the solution going to come from? That's a technology solution rather than a regulatory solution.
Yeah. Well, if I left the impression that spam is not a problem, or that I don't get really mad about the amount of spam I see in my inbox, I left the wrong impression. My point in that slide was to say that we are making a lot of progress, and that regulation, where it's been introduced, has not been very effective, whereas technology is being effective. We are seeing a lot of spammers going into other businesses now because they're finding that only 1 or 2 out of every 100 spams they send are being delivered. So there is progress being made. But the long-term answer is probably in universal authentication. If we have ways to track back and actually know that somebody sending you something is actually authenticated. You may not know exactly who the person is, but if they can authenticate themselves so that they are a member of a business association, or if they're a student at a certain college and therefore there's some way to at least know that somebody knows who they are, even if you can't find out who they are. That will help hugely. But my point in that is that there's an arms race going on, and the technology is moving a lot faster than the regulation, and the technology, I think, is going to be the way we answer that problem. But I'm sorry if I left the impression that spam wasn't a problem. I just wanted to leave the impression that it would be a much bigger problem if we hadn't made the technological progress we have made. And I agree with you. Congressmen listen to the slowest common denominator. The individual who just doesn't, is at the trailing edge of technology development and adoption. And we have to make sure our solutions meet that person's need. Another one of the jobs I have in my spare time is I'm on the advisory committee for the Pew Internet and American Life Project. And they do some very sophisticated telephone surveys of Americans about their Internet use. And we have found that there is a group of people who are just getting sick and tired of the net. It's not just spam. It's often virus problems. It's the cumbersome nature of the technology they're using. And they're actually getting turned off by the net because of that. So we have to address those problems. And otherwise, we're not going to get the 100% usage that we've had with the telephone or the television or the radio.
I think there are 3 microphones.
Okay.
I'm just going to go 1, 2, 3.
Well, okay, I think that I'm Leif Laaksonen from Finland, the IT Center for Science in Finland, and let me first thank you for the inspiring lecture. I'm not sure I would agree on everything, but it would take such a long time. But I would like to come back to one of the original things. I think somebody, the first questioner here, asked about the scientist, because I think there has to be a lot of changes in the way science is conducted in the future as well. I think the science community works in a very old-fashioned way today. So I think the most scientists that compete through publications, and they are trying to push their own career. And I think that's some things that has to change as well. So the way science is conducted in the future has to change as well. So we might be able to fit in the IT support we are all building into it. That this is a challenge as well, because otherwise we might end up in a situation that we have marvelous tools available, but people don't willing to apply or use them.
Well, I have another 30-minute lecture on that question. IBM's been a real promoter of what we call collaborative innovation. It's all about assembling teams that can share computing resources, share ideas, develop new technologies, and new uses of technology. We make a distinction between invention and innovation. Invention is the creation of the new technology. Innovation is actually making it useful for real people and getting it out there. And both of them require teaming. I think the academic community is doing a very impressive job in this area. They've made a lot of steps in certain disciplines. They've made a lot of progress in finding ways for dozens or even hundreds of people to work together. If you look at the high-energy physics community, for instance, typical papers will have 100 authors on them. The whole first page will just be names and affiliations of all the people who have contributed in some way. And they do that partly by using Access Grid and using the grid to do their computations. So I think there's a lot of progress being made. The talk that John Delaney gave yesterday, I think, is a wonderful example of the new paradigm, how different people in different disciplines are combining different data. One of the people on the slide he showed of contributors is my brother-in-law, who's a geophysicist at the University of Washington. And he did a project where he teamed up with a marine biologist who had been collecting data on whale patterns, and he used seismic data. They have these ocean bottom seismograms that actually pick up the sounds of whales squeaking by. And so by combining this geophysics data with the information about marine biology, they were able to track the levels, where these whales were going, and learn all sorts of things that they couldn't have done if they just focused in one discipline. So there's some very cool things, very serendipitous things that come out when you combine data and combine disciplines. And so I think the academic community actually does better than anybody else in this new world of collaborative innovation. The biggest problem we see right now for innovation in the IT community is the hyperactive intellectual property lawyers. You may get a sense that I'm not an intellectual property lawyer, and I don't have any, and none of my friends are anymore. But too many universities now are trying to patent every little thing that comes out of their engineering departments. And this makes it very hard for IBM or any other company to work with the universities and to do collaborative research that will lead to the next big thing. And so we're pushing universities and pushing other companies to work more on an open source paradigm. If we let everybody patent everything, the intellectual property lawyers will be very rich and the rest of us will be very poor.
Halfway back.
Way over there.
Yep. Yes.
Okay.
Dave Wilson, HEANet. If it's the case that we should use technology to solve all these legal and political problems, does that mean we should not oppose digital rights management software?
You have to first ask what the problem is we're trying to solve. I think the most exciting thing that's happening is the open source and the Creative Commons movement. It may be very well that digital rights management is a solution to a problem that's going to go away. I think more and more people are realizing that the old model of copyright control isn't the best way to make a lot of money. We see a lot of individuals who are just blogging away, giving away all these good ideas and all this content, and making a huge amount of money, either from the advertisement on the website where they give away their content, or more likely they're making a lot of money by charging $5,000 or $10,000 a day to be a consultant to a company that has been impressed by their wisdom. And so that's a completely different business model than the lock it up, charge per pay-per-view kind of model. I think I made pretty clear I'm not in favor of a pay-per-view world. We don't want a world in which there are no choices, where everything is protected by digital rights management, where there is no fair use. We want a world where you can give away your content and not have a webcaster claim they have control over it. But there's room for a lot of different models here. And you know, IBM has spent 20 years trying to develop some digital rights management technology that our customers would buy and would use and would also meet the needs of consumers. And so far, nobody's found that solution. But yeah, I mean, I think you should be adamantly opposed to digital rights management solutions that don't meet your needs. And I'm very glad that we haven't seen a pay-per-view world develop. And as I say, I think in the end it's not going to be the business model that wins. Another bumper sticker I like to use is that in the 200 years since copyright was developed, the cost of sharing bits has decreased by a factor of about 10,000. And the pace of innovation has certainly increased. And so it would seem logical that since it's so much cheaper to share information, we wouldn't need to provide so much incentive and so much copyright protection. And it would also seem that since the pace of innovation is faster, we wouldn't need to have such a long copyright term. But in those 200 years, in the U.S., we've increased the copyright term from 14 years to over 120 years. So something's not quite right there. And I think that's why we are seeing these new business models like the Creative Commons approach that are providing very viable ways for people not only to provide content over their blogs, but also to create movies, to create some very interesting new media that is open sourced and available to the world.
JP, I think.
Hi, JP Velders, University of Amsterdam.
Okay.
Here.
Oh, right there. Okay.
Found me. The whole net neutrality thing, how do you see that play out, especially if you look at carriers and telcos trying to keep on to their common carrier status? Because I think both are at odds with each other.
Yeah. Well, in the U.S., the Supreme Court has basically decided, and the Supreme Court and the FCC have decided that common carrier rules do not apply to broadband, and that we have a different model in this new world. The real question isn't whether we can write rules about net neutrality and whether we can force companies to be open. Because I, having worked in government, having seen the legislative process, which is even more dysfunctional in the U.S. than in most countries, I can tell you that the rules would not be written in a way that works today, let alone in the year 2011. They would be written from a perspective of somebody who understands point-to-point telephone networks. They would not really reflect the reality of the Internet today. And there would be all sorts of unintended consequences. There would be cases where I'm sure that the regulations would have exactly the wrong impact. They would actually end up harming new entrants and making it more difficult for new ideas to get into the marketplace. So I don't think we're going to, in the U.S., it's very unlikely that we're going to see any kind of net neutrality rules that actually change the architecture of the net. I think the most likely, if there's anything that happens in this area, if there's any kind of net neutrality legislation, it may be some kind of consumer notification that says ISPs must tell their customers just what kind of Internet service they're getting and reveal that certain websites are off limits or that certain sites are favored over others. And if that happens in a competitive market, I think we'll have net neutrality pretty quickly. Because customers want everything. They want the whole net. They want the ability to use their own software or their own hardware in the net. So I think in increasing the market pressure for an open net may be the right solution here. The other reason, though, I think it's unlikely to see, we're unlikely to see legislation in the States is just because there are so many issues floating around right now. Net neutrality is just one of about 10 very big telecom policy fights, and given that we're in an election year, given that there are a lot of other things to worry about, I just don't see it happening this year. There are proposals in other countries, though. I've seen draft language in France and in the Netherlands that would actually try to write into law what net neutrality is. And I think that actually focuses the attention in the wrong place. It really focuses on the design of the network when we should be focusing on the structure of the marketplace and how to create competition. Because in a competitive marketplace, we're going to have an open network. We're going to have a network of networks, and we're going to have more content coming from more places than you can possibly imagine.
I think there's an interesting possible effect in Europe in that I suspect any provider who doesn't do net neutrality will become liable for that content they do let through, which, you know, if they do if they don't do net neutrality, they might lose common carrier as well. Yeah. Mike was waving a hand. No, he's no longer waving a hand.
There is one place where net neutrality becomes a real serious problem, and that is when telephone companies start cutting off services like voice over IP. And the Internet Society has been very adamant in fighting those countries where the phone companies have tried to block Skype and voice over IP, because that clearly is just, that completely undermines the end-to-end nature of the net. And it's totally anti-competitive. But you don't need a new law for that. That's not net neutrality. You just use antitrust laws. So,
any other questions?
We solved all the world's problems.
I feel guilty that I've seen no hands over this side. But I think it really is because there have been no hands over this side. So.
Well, I know how late the party went last night, so I'm very glad any of you showed up here at 9 o'clock a.m. to be part of this.
Okay, I think we're in fact just about on time. Coffee will be served in about 5 minutes outside in the sunshine. I'd like to particularly thank Mike for filling in and extending the interest of what he was told to be interesting for 45 minutes. As far as I'm concerned, he's been absolutely fascinating for 90 minutes. So very many thanks.
Well, as I mentioned...
Allora,
soprattutto là sulla
il problema, sai qual è?
l'ho spiegato,
Che-
si è spento questo, ha parlato di quell'altro. Tu lo puoi.
Prova, prova. 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 Prova, prova. 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 Sì, prova. 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 Sì.
On a CD or on a pen?
I'm sorry, what?
Have you got it on a
I've got it, no. I got it on a thumb drive. Shall we try putting it on here?
yeah, but I should finish this stuff first.
Okay.
And I don't know how much it takes.
I don't worry about my PowerPoint slides, although I want to test them. But they came from an IBM, so probably should be fine.
Let it go, I hope.
Is there someone in here at 11? I'm trying to find a quiet time. Well, I still want you to know my all-time favorite hotel in Italy was the Hotel Francesca. I loved it there.
So,
These don't look good. But I need that one, and that one. They don't look like they have players associated with them.
this is Windows Media.
Yeah, we'll see if it works.
Windows Media, well.
Because a couple
real.
of, yeah, that one's real. This one's Windows Media. This should be, one of them has to be, I can't remember what it's called, WinDVD something player. Yeah. I don't know why it does that. I had to associate it with a different player because it's too choppy. No. I can open my laptop if you want and tell you what player is associated with it.
This one does not do that really. Better you do it from your own.
Okay.
That's fine.
Okay.
If it works with the projector. No association.
Yeah, we'll start the other way first. Let's see how we do. The problem might be getting audio.
There is the audio.
Is there the little input?
Yes.
Okay. Okay.
Video first.
I don't know. It's brand new. I think it's right there. Yep. Last that mean it's on the screen? Yes, I think so. Aegon, do you see Colorado?
No, I don't see any. Yes, I do. Big black hole. Oh, no, I have my projector switched to...
Yeah, okay.
Okay, okay.
So, right, you can see mountains over there.
That one is not so.
Good.
Okay.
Let's let it boot up a minute.
Yes, that's your... that's all.
So far, so good.
The audio is done here.
It's over here. Oh, it's here.
Yeah? You got it?
Is that your band, Diego? Is that your band?
Yeah. Those are my new wives.
Yeah. What's Monique's email address? So we're getting something. Now it's good.
Hey, Claudio, we have video, just not audio, but it might just be me.
The other makes a bit to switch.
Yeah, I was going to say, it might be very simple.
It's a very exciting prospect. Here in Miami in the studio with me this evening is our coach for this project, Ivan Chan, who is the first violinist of the Miami String Quartet and a member of Florida International University. So if everybody's ready, let the music and the coaching begin. Anne Marie, you want to...
Hey, Claudio.
Hey guys, you hear me? Excellent, very, very good. Since we have limited time, I'm sorry I have to stop you right away.
At first I was a bit wary, but very soon I saw the immediacy of the video presentation and also the high quality and clarity of the sound.
It's very strange.
At first I was a bit wary, but
The audio and video on that one are like, no, it's very strange. It starts out sick. How strange.
At first I was a bit wary, but very soon I saw the immediacy of the video presentation and also the high quality and clarity of the sound.
You just played this on my before I came in. It was fun, but it's.
I almost forgot that there were cameras there.
It's like behind.
And
But you have the data here, yes. That's not the link. Or that's only the link.
Well, 2 out of 3 is not bad. Are you about to present?
Yeah.
Oh, get out of your way.
There's the next session, so.
Okay. Well, thank you. 2 out of 3 is not bad. I don't know why that third one is doing that.
I don't know either. I can try to play it on mine if you want to see it.
That would be interesting, and I've got it on that little thumb drive, so. Thank you, you're a doll. In which case, maybe I'll just, well, it doesn't matter. See, I could do my PowerPoint from there. Just have this queued up with the clips. That might actually be nice. Grazie, Claudio. As always. Good luck.
was out having coffee with David just a few minutes ago. So he was here.
Yes.
Well, they had terrible feedback problems with that in the last presentation.
Last.
It's been fixed now?
No.
Okay. Well, that's what we were just discussing. Test level. So did the problem start arising when you stood up? Okay. So far, so good.
Was that pretty audible?
You were fine. I was back there.
It's such a lovely sunny day outside with people having croissants and ice cream.
Oh, I missed that part.
Yeah, I was just coming back and I saw all this ice cream being given out, so I thought, well, I can eat that while Steve's talking.
But did you bring any for us? No.
I didn't have 4 hands. Oh, if you want to, yeah. I mean, that one is, that's the one where I'm supposed to download it from the website, but if you've got, is the version different on the site? Yeah, I prefer, you prefer to use your own. Yeah, you prefer mine because you know the controls. That's fine. Yeah. And what I'll do is
Also, we can get Office on the Mac with PowerPoint is you get a presenter's view, which shows you note pages and the previous slide and the next slide.
Will you do that? And I'll put Mike's up. Do you want to do it from your own?
I can do it either way.
I mean, it's up to you, totally up to you. We can either display it on this one, or we can just move the cable to the back of yours, and you can use yours. It doesn't matter to me either way.
Yes, that's fine. So you see what I get now when I go to this is that shows up there, but I have all
Okay,
that.
so you've got before and after as well.
Yeah, so you've got the context. that
Yeah,
way.
excellent. people are starting to come in. I think we're going to start about 5 past, actually, aren't we? Really?
The schedule said that.
Yeah, that's just something we have to probably start about 5. You've got a microphone. This one. You've got the, right, okay, this one. Okay. What time do you make it now?
It's coming up on 3, well, 2 after.
Yeah, I make it, yeah, about that. I'll give it 1 minute and then we'll start. Okay. And it doesn't matter if we go 5 minutes into lunch because we've got an hour and a half for lunch anyway, haven't we? So, yeah, so we'll look at it. Well, good afternoon, almost, ladies and gentlemen. I hope you enjoyed your coffee break in the sunshine. We are running a few minutes late now. I make it about 4 minutes past 11, so I would like to start. And the first speaker today is Dr. Stephen Kent, who's the Chief Security Scientist from BBN. Now, who better could we have to talk on IPv6 security than Stephen, since he's the author of 4 of the IPv6 specifications. He also is the previous chair of the PKX group and is a very popular speaker on PKI technology as well. So without further ado, I'll hand over to Steve, who is an excellent speaker, and I'm sure you'll all enjoy what he has to say.
Thank you, David. Well, as per the title, we're going to talk about IPv6 security, and the specific part, the primary feature of IPv6 that is security-centric is IPsec, though IPsec itself is not specific to IPv6. Essentially, every laptop in the audience today probably has IPsec available on it because we designed it in a fashion so that it could be used with both IPv4 and IPv6. IPsec is not a protocol per se. It's an architecture, it's a suite of protocols. And the 2 primary protocols that provide protection for traffic are something called ESP, the encapsulating security payload. We could have used a marketing firm to give us a better name for that. And AH, the authentication header. And in fact, I order them in that fashion in this slide because over time we've come to care less about AH and more about ESP because we've broadened it in the past and made ESP powerful enough that there are very, very few circumstances under which AH is really necessary. We also have a protocol, IKE, that is designed to provide a collection of management functions with regard to putting cryptographic keys in place and exchanging the parameters that we need to characterize how we're using IPsec. IPsec is very flexible and very powerful. And so every time we create what we call a security association, we have to negotiate the parameters that characterize how we're protecting traffic and what traffic is being protected. It's reasonable to step back and ask, why did we choose to develop IPsec? And that starts with the question of why protect traffic at the IP layer. We have a number of layers at which we could do this. But the IP layer itself offers unique advantages. It's the lowest layer in the protocol stack that is independent of any network technology, which is, of course, why Vint Cerf, Bob Kahn, and Al Gore invented TCP/IP long ago. So it's right at that point where it is completely independent of underlying technology, which is why we can use IP over any network. It's also the highest layer in the stack that is unquestionably protocol application dependent and protocol suite independent. Now, saying it's protocol suite independent is a little bit of a fib. There was, back in the time frame that Mike alluded to in his talk in the early 90s, we had protocol wars between the TCP IP stack and another stack that shall remain nameless. In history, we say that the winners of battles or wars get to write the history. In protocol wars, the winners tunnel the losers. And so because of that, we are, for all practical purposes, protocol suite independent. IPsec allows end-to-end protection, which is what we idealistically say you should want to do. But in reality, we don't always get to do that. In fact, we frequently are doing end-to-gateway or even sometimes gateway-to-gateway security because the folks responsible for this find it easier to manage in that fashion. And so it's important that IPsec does this from the start architecturally. It's not something that had to be added in later. We intended it to work in that fashion from the beginning. There are several important pieces of IPsec that are necessary to really understand what's going on. One of these is a security policy database, the SPD. And the idea behind the SPD is that for all traffic that is crossing this magic IPsec boundary, you have to say in the SPD whether the traffic is to be bypassed, it's not being afforded any protection, whether it's discarded, that is, you're not going to let it cross the boundary, or whether you are protecting it using IPsec protocols like H or ESP, and if so, in which fashion it's going to be protected. So that's a central part of the IPsec model. Security associations are how we offer the protection. A security association is just a kind of a connection, if you will, although it doesn't have the connection qualities of something like TCP. And the security association is unidirectional, so we create them in pairs typically to provide support for what is typically bidirectional traffic flow. And we associate with the security association all the parameters that each end of the association needs to be able to process traffic appropriately. Finally, there's a security association database where we keep all the data about security associations, the state information. And one way to look at this is to say that the SPD represents potentially what you can do, and the SAD tells you what you are currently doing. It represents the instantiated security associations. We added, in the latest round of IPsec standards, hopefully the last ones we'll have to do, a new database called the PAD, the Peer Authorization Database. And this came about because in looking at what had been done previously, we realized there was a gap between what IKE did for security association management and what the SPD said, and we didn't glue them together properly the first time around about 7.5 years ago when we published the standards. So to fill in gaps there, that vendors, of course, had been filling in themselves in a not uniform fashion, we created the PAD. And the way to think of it is that the PAD is where you are putting information that will be used by IKE, directing it in terms of who the peers are, how they'll be authenticated to you, and then what controls are imposed on what they get to assert about the security associations that they're establishing. The basic model for IPsec is the one that you see on the screens at the moment. So we draw that magic little IPsec boundary, and for all the traffic, as I said before, the SPD tells us whether we get to bypass it, whether we discard it on one side or the other, or whether we force the traffic to go through AH or ESP processing. You'll also notice that IKE appears on the diagram on the protected side of the boundary, and that means we make explicit provisions in the SPD for IKE traffic to cross that boundary essentially as bypass traffic because it's not protected with ESP or AH. It has its own internal protection mechanism. In terms of where IPsec fits in the protocol stack, it's really a question of how it's been engineered in. Today, we tend to have native IPv4 and v6 implementations with IPsec built into them, which is the preferred approach. It makes for a more efficient implementation. However, that's not the only game in town. And in fact, what we had before then as a retrofit approach was to slip IPsec in under the IP implementation and and above the local net interface that you might find from a network interface card. And that kind of bump in the stack implementation, as we called it, was again something that we recognized from the beginning would occur, and so that's part of the architectural description. It's not a hack. From an IPv4 and v6 standpoint, we see a slightly different view of things. For IPv4, IPsec is this other thing. It's not intrinsic to that set of protocol descriptions. But for IPv6, as the little dotted line suggests, it is an inherent part of IPv6. You can't have a compliant IPv6 implementation without IPsec. IKE sits way up at the application layer, being invoked as required to create the security associations on a dynamic basis. In fact, in many implementations, you see this in terms of how the implementation of IPsec is done, that IKE itself may live outside the kernel, for instance. When we designed IPsec, we looked at different ways that it might be deployed. And so we have the notion of end-to-end protection on individual hosts, and that can be a native implementation in the operating system, which is what you find today in Windows or in Mac OS and is available in Linux, etc. A bump in the stack, or what we call a bump in the wire implementation. And a bump in the wire implementation, for instance, could occur if you put IPsec in the network interface card. The reason that is potentially attractive is it can provide us, under the right circumstances, with the highest assurance for IPsec implementation, because it's not going to be subject to the bad things that may happen in your operating system environment, given that the operating systems we have are not the most secure things in the world. So that's still a motivation for people who are very concerned about assurance to have an implementation which is not integrated with the operating system, because that's a drag in terms of the overall assurance that we're going to get. We can also have a collection of hosts behind what we call a security gateway that are afforded protection in a more or less uniform fashion. And that's the way we see IPsec used frequently in an enterprise environment, is it's integrated in with a firewall. Firewall vendors now offer IPsec and have for several years. Or some people offer IPsec devices that are high performance devices specifically for this implementation, and you can get very good performance in that fashion. So with those two choices of an intermediate system, a security gateway, or an end system, we have three choices of peering relationships: a pure host-to-host, a host-to-security gateway, or security gateway to security gateway kind of peering relationship. And again, all of those were anticipated when we designed IPsec. And so if you look at the current set of standards, in particular RFC 4301, we talk about what is required in each of those devices, end systems versus security gateways, to be compliant, to make sure that they will all play nicely together. We've also seen a broadening of the range of applications for IPsec to things that fit this model but are slightly different. For instance, PPVPNs, provider provisioned virtual private networks, which may or may not succeed in the marketplace, but there are vendors who have been building them, and we made some changes in the latest version in 4301 to accommodate some of the things they needed to do. Also the notion of overlay networks, where you're creating your own network on top of the public internet. In that case, using IPsec as a kind of protection on a link-by-link basis, which was not the kind of thing we originally envisioned for it, but it's a reasonable thing to do, and it required relatively few changes to the architecture document to say how you would do that. So we've added that in. Again, from an implementation standpoint, the native IP with IPsec on one side, in the middle the bump in the stack approach, and on the other side the bump in the wire approach, which could be a completely outboard implementation, or could be, as I said, on network interface card. The protocols that I've been talking about are described in these RFCs as illustrated on this slide. 4302 for AH, which replaces 2402. 4303 replacing 2406. IKE had a whole series of RFCs the first time around. It was a very complex protocol. IKE version 2 has fewer documents that standardize it, and it's better described, and implementers find that it's an easier thing to implement and interoperate with. So hopefully we'll see more people making the transition to IKE v2 over the next couple of years. And then the RFC that deals with the architecture, that says how all the pieces play together that provides essentially the state machine kind of descriptions for IPsec is now RFC 4301. So let's look in a little more detail at the notion of security associations. As I mentioned earlier, an SA is a unidirectional construct, but Ike always creates them in pairs because we tend to deal with bidirectional protocols for the most part. What an SA does in terms of the state in the security association database that goes with it is to characterize the traffic that's going to flow over it in terms of source and destination IP address, if it's, the protocols to which it will be applied, and ports if applicable. And we've interpreted in the latest version ports more generally to deal with some other things. For instance, types out of ICMP error messages and appropriate fields for IP mobility headers, things of that sort. Having described which traffic is going to be protected by a given security association, we then say how that protection is to be afforded. So we say which protocol is to be used, AH or ESP, which cryptographic algorithms are to be employed. We store the keys, and we talk about the crypto periods, that is, the duration over which the keys will be used, either in time or in traffic volume, and maintain some information for anti-replay purposes. One of the nifty features about IPsec is that we allow local system administrators or security administrators to decide the granularity of protection that's afforded. So we can have one security association that will carry all traffic between two sites. And if you're an enterprise user trying to construct a tunnel to carry all the traffic between headquarters and some remote office, this is a perfectly fine thing to do, and you can just do that. If, on the other hand, you're an individual and you want to have a separate security association for every TCP connection you create, even if you're creating it to the same other point, to the same destination, you can do that as well with IPsec. And that requires that we adopt a naming scheme for security associations which can span that kind of granularity from individual TCP connections or UDP streams all the way up to all traffic between two sites. We do that using a 32-bit value, an SPI, a security parameter index, and that value is chosen by each end of the association and is communicated to the other end. And you're basically telling the other end, when you send traffic to me for this security association that we're now setting up, put this tag on it so I'll know that it's that particular traffic. And for unicast, this works just fine. For multicast, things are obviously more complicated, and we don't have time to talk about that today. In the multicast environment, though, we have to use slightly different techniques for labeling the security associations. But that approach distinguishes what we do here in IPsec from many of the other protocols that are around, because many of the others are tightly bound in. The granularity at which they offer protection is tightly bound to where they fit in the stack. So if you were to look at SSL, for example, it has an entirely different approach to dealing with it because it's sitting on top of a TCP connection. And this diagram is just illustrative of the fact that even between the same two endpoints, we can have multiple pairs of security associations in place at the same time. And one of the reasons that we would do this is not only the issue of I want very fine-grained security for access control purposes, but for transitioning. When we expire keying material for a given security association, we want to roll over to a new security association, yet we would like to not disrupt traffic flow. So what we do is we create the new security association pair and then migrate the traffic to it. And that's the most obvious reason why you want to be able to have two sets of security associations between the same 2 points at the same time to allow for that easy, seamless migration and then move the traffic off of the old one, kill off the old security associations. Encapsulation is a feature of protocols in general, and IPsec is no different in that regard. Although the way we do encapsulation, frankly, is much cleaner in the ESP context than it is in the AH context, which is one of the reasons that we don't really like using AH anymore if we can get away with it. And in most cases, in fact, you don't need to use AH. In order to see how that works, we'll have to look at each of these protocols in order. So for AH, this is the format. We start off with an 8-bit field for the next protocol. Why? Well, in an IP header, we have an X protocol field, and that tells us, for demultiplexing purposes, whether we should hand this traffic off to TCP or UDP or ICMP. But when we apply IPsec, it becomes a kind of sublayer, and so that next protocol field in the IP header is going to point to IPsec. It's going to say that it's AH or ESP now, which means we still have to carry what the real next protocol is going to be so that we can demultiplex properly. We then have a length field. I won't even try to justify why it's computed the way it is. It has to do with when we originally developed these protocols long ago, over a decade ago, people wanted to view AH like an IPv4 option, and so the length field is computed as though it were an IPv4 option. Then we have 16 reserved bits. Now, this is giving away secrets of protocol design, but in an audience like this, I think that's appropriate. They're reserved not because we have some notion of, hey, we'll need 16 bits for flags or other fields in the future. They're reserved because we want the next field to start on a 32-bit boundary, because, hey, we like doing that. And so that's why they're reserved. The SPI for labeling a security association is the next 32 bits. And then after that is a 4-byte sequence number. We have sequence numbers that are applied on a per packet basis. So it's not like TCP, which is counting bytes in a stream. It's just each packet being serial numbered. And we do that for anti-replay purposes. Because we live at the IP layer, we assume that packets may arrive out of order, and so we can accommodate within reason out of order arrival. But we don't want someone taking a perfectly legitimate IPsec protected traffic, making, a million or so copies of it, and sending it at us and making us do all the cryptographic work of processing it and then passing it on. Because, duplicates are not going to be really useful. One is enough in this environment. So that's why we have that field. And then after that is an integrity check value that's variable in length, but as you can imagine, we do like to have it be an integral multiple of 4 bytes in the case of IPv4, 8 bytes in the case of IPv6. Now, the packet structure here shows you why the encapsulation isn't quite as nice as it could be. And I didn't even put up a v4 version, I just focused on v6. In v6, we have a very complex header structure potentially because we have hop-by-hop options and end-to-end options and extensions. And AH could move around in there depending on what you were trying to protect. So you can put certainly end-to-end options and extension headers behind AH and thus get the integrity protection and authentication that it provides. The problem with AH from the beginning is that it was designed to also protect certain fields in the IP header, and that header is on the other side of AH. And that means that when you're computing the integrity check, you're sort of hopscotching through the header, and obviously that's inefficient, and frankly, it's ugly. So that's one of the reasons we prefer not to use AH. It's hard to do this at really high speeds because of that. And then, of course, after that, all the upper layer protocol header and data, transport layer, et cetera, is all protected, and that's fairly straightforward. ESP is a little more complex in its header format, but it's much cleaner, more straightforward in terms of encapsulation. So in the case of ESP, we start off with the 32-bit SPI, we follow it with the 32-bit sequence number, and then we have whatever we're protecting. So we encapsulate it in a very clean fashion. Everything we're protecting goes inside of this envelope of ESP. Then the last 2 bytes that are protected include that next header field that we had out in the clear in AH. Well, that's fine because it wasn't encrypting anything. In the case of ESP, you may be encrypting the data. It's optional for confidentiality purposes, and so there's no point in giving away that information about what protocol is being carried. And if you're using the padding function, which you might have to use in order to get everything to line up nicely on 32-bit boundaries at the end, there's a pad length field. Following that is the integrity check value, same format, same algorithms that are used for AH are also defined for use with ESP. So we can just see immediately this is a more straightforward kind of encapsulation. And if we look at the packet structure here, we see that it's much cleaner as well. Now, one of the interesting things about ESP is that we allow you to do 2 things if you wish. Sort of full function ESP provides confidentiality for data via encryption, and it provides integrity and authenticity for the data through the use of the integrity check value. We're doing 2 operations generally. Which one do we do first? Turns out that this is not an arbitrary choice. There's a very good reason for picking one over the other. And what we chose to do was to encrypt first and then perform the integrity check on the ciphertext if we have encrypted, which drew some questions from some people at the time. Now, from a transmitter standpoint, it doesn't make any difference. You're going to do the same amount of work on every packet if you choose to do both operations. So this is purely a receiver-directed thing. Why is it important? Well, the receiver's seeing packets coming in. And if the packet comes in, what's it going to do first? It's going to look at the sequence number. If the sequence number is a duplicate, it gets to throw it away and does no cryptography whatsoever, which is very efficient, although the fact that you threw it away isn't such a great thing to have to do. What's the next thing it's going to have to do? Well, in this case, because of the order in which we did the operations, it can perform the integrity check. And if the integrity check fails, there's really no point in decrypting the packet. On the other hand, had we done integrity and then encryption at the transmitter end, you'd have to decrypt the packet and then do the integrity check, so an adversary could force you to do both sets of those crypto operations. Why let an adversary do that? So we picked the order in which we're doing this very carefully for this purpose, and the slide illustrates that. Let's talk briefly about IKE. IKE is relatively complicated. The thing it's trying to do is fairly simple. What happens in IKE is that the application entity that represents IKE at each end of the security association establishes a secure connection with its peer. And having done that and put keying material in place to protect that, it can establish subsequent child security associations, one or more of them, to actually protect the traffic on behalf of the subscriber. So first of all, you have to authenticate the other party, negotiate which algorithms you're using, etc., and then you can put in place one or more child essays below that. Now, I won't go through all of the details here, but this is what IKE's trying to do. First of all, it uses ephemeral Diffie-Hellman key exchange. Why ephemeral Diffie-Hellman? Because we want perfect forward secrecy. The property that this has in the IPsec context is that there are no long-term secrets held by either peer which, if they are later disclosed, somebody breaks into the implementation and yanks them out, will allow previous security associations to be decrypted. That's as good as it gets. And so that's why we use ephemeral Diffie-Hellman. From the ephemeral Diffie-Hellman exchange plus nonces thrown in by each end, we use a key derivation function, which is based on one-way hash functions, to go ahead and generate a bunch of keying bits through a technique that we refer to technically as slicing and dicing. And that's how we get the bits for encryption keys, integrity keys, etc. We also use separate keys for encryption and integrity in each direction because each security association is treated independently. So all those, and that intrinsically provides some nice features. It means that an attacker can't take traffic in one direction, turn it around, and try and send it back to the originator because the keying material would be wrong. So clearly that will just instantly fail. We don't even have to have a flag in the header to tell you which direction things are going because it will just die in that fashion. What IKE also does for us, in addition to the cryptography of setting up these associations, is it's negotiating parameters. It's negotiating the SPIs, which protocols are to be used, the traffic selectors that we'll talk about shortly, the algorithms to be used for confidentiality and for integrity, if you're using both, which mode, and we'll talk about shortly, and the lifetime of the security association, as I said, which is measured either in actual time duration or in terms of traffic volume. These slides, and I'm not going to go through all the details, show you what IKE's doing. So the initial step, the exchange between the initiator and a responder. Notice we don't use terms like client and server here because this is a peer protocol. We have no notion of client or server in it. Are sending over the Diffie-Hellman ephemeral public keys and nonces, and also an opportunity to issue a request for certificates because IKE can authenticate either party in a variety of ways, but we do make a lot of provisions for certificate-based authentication. Having done that initial exchange, they have keying material in place, and the second exchange between initiator and responder is integrity protected and encrypted. So at the point at which you assert who you claim to be and send over data to authenticate who you claim to be, a passive wiretapper can't even see that information. It's already been encrypted. So that provides some level of traffic flow confidentiality. And then at the end of the second step, with 4 messages having been exchanged, you have the material in place to create the first child security association. If you have to create additional ones later on, or if you need to rekey the one that was initially created, then we use another pair of messages specifically for that purpose. So those are the kinds of messages that are being sent back and forth by Ike to do this. I mentioned the term mode a moment ago. In IPsec, we have a lot of choices about how we can use it, and we have to have terms to describe what those choices are. So, for instance, starting at the top with the datagram we're going to protect, we could use AH or ESP, and it could go directly behind the IP header. We could use them together, and early implementations seemed to default to this, and frankly, there was never a good reason to do that. We fixed that. We discouraged that in the latest architecture. We don't require support for it. Or you could do it nested, and there's certain circumstances under which that made sense. Now, at the bottom are the two modes that I referred to, transport and tunnel mode. The first, transport mode, is the most efficient. It says that we have the IP header we started with. We only have to adjust it in terms of next protocol and total packet length. Then we put in the AH or ESP header, and then we protect whatever is above it. However, in certain contexts, we have to create a new IP header, then put in AH or ESP, and then take the entire original packet, header and all, and encapsulate it in that fashion. And that's what we call tunnel mode. Why do we do both? Well, if you're going just between two hosts, transport mode works fine, it's efficient, it's a reasonable thing to do. But if either end of a security association is a security gateway, then at least the security association that terminates there needs to be tunnel mode. It needs to have that inner versus outer header so that we can do things properly. And for simplicity, we require both security associations to be tunnel mode under those circumstances. So here are some examples. This one going between host 3 and terminating at router number 2, obviously a tunnel mode association because one end is a security gateway. Similarly, in this case, going between host 1 and router number 3, the same sort of thing would apply. And the last example here, if we have some road warrior, a mobile user, with a peer-to-peer kind of association between that user and host number 1, well, that could be a transport mode association, but nothing prevents you from doing tunnel mode. And sure enough, every few years, and this appears to be one of those years, we have someone send a message, even though the working group is now closed down, and say, well, do we really need both? And the answer is, well, we could have one or the other, but last time we checked, we had about 50% people wanted just one, and the other half wanted the other. That's why we have both, is because we can get agreement on which one to kill off. Now, one thing that is often, I think, misunderstood about IPsec, so maybe we need better PR here, is that IPsec is all about access control. It's not primarily about encrypting traffic, it's about access control. And that's because when you look at what people do, especially in enterprise environments with regard to security, that's all about access control. Why do you have to authenticate? Well, because we want that input for an access control decision to see if we'll let you connect to the network or to a particular host in the network, etc. If you look at what a firewall's doing, it's taking inputs in the form of source and destination addresses and next protocol field and port fields and making an access control decision on a per packet basis to decide if this packet's allowed to transit the firewall. So IPsec is in fact about access control. That's why we have the security policy database. And we've also had the discussion of, well, couldn't we make IPsec simpler and just let it do the crypto stuff and let firewalls do firewall things? And the answer is we could, but it would not provide equivalent security. And we'll see why that's true in a moment. But before we do that, I wanted to show you the kinds of example, a couple of example entries of the sort that we would have in a security policy database. The first one is set up to provide security for telnet traffic. And so it's saying if you're going from anywhere in this range of addresses to a particular destination, the protocol is TCP, protocol 6. The source port is any port that the destination is port 23 for telnet. Then I want an ESP association. I want it in tunnel mode. I'm going to use a particular form of encryption, AES 128-bit keys in counter mode, and HMAC SHA-1 for integrity. And that would be a complete description. On the other hand, the next entry is a bypass entry. And it's a bypass entry saying, yeah, traffic going to this destination, which happens to be a DNS server, should just be bypassed, as long as it looks like it's DNS traffic. So these are the way you construct entries for the SPD. And the reason that we can't do these separately, why don't we just take the access control part and the crypto part and separate them, is that by putting them in the same system, we manage to keep the SPI, which is the tag for the Security Association, with the data after we've cryptographically processed it, and thus we can check to see if the traffic that is arriving on a Security Association is consistent with what we negotiated with our peer was going to be okay traffic to arrive on that association. If we split these two apart and we have an Ethernet cable between them, let's say, then the traffic would be cryptographically processed, handed to the firewall, and the firewall would be saying, if it really came from the source indicated, I have a rule that says it's okay or it's not. But do I know it came from that source? No. Somebody with whom I have an association could have put in the wrong source address on the packets, and thus I'd be spoofed. And that's unacceptable. There's no need to do that. So that's why we bundle these two together. Now, we have just finished a long, arduous process. It completed with the issuance in November of last year of a whole new suite of IPsec standards that were updates. What did we change? Well, we made changes in AH and ESP to have bigger sequence numbers. Why? The thing that Mike Nelson pointed out earlier, the network's getting faster all the time. 32 bits seemed like a lot. I was there when we thought 32 bits was plenty enough for IP addresses, what can I say? You got to live with these things. It seemed like a lot at the time. So we said we'll have more bits for sequence numbers because under worst case situations with a 10 gigabit Ethernet interface, you could exhaust the sequence number space in about 6 minutes. And that seemed silly. And so, hey, let's just throw twice as many bits at it, but we don't want to be accused of being profligate. And so what we did was we said, you'll still carry only 32 bits, the low order 32 bits in each packet, and we'll maintain the upper 32 bits of the 64-bit counter at each end and use it in the integrity check. And that way, you'll just have to propagate carries into the upper 32 bits every 2 to the 32-bit packets. And that works fairly well. I will admit there is a circumstance under which we can get into trouble. If you have a security association and you lose 2 to the 32 packets in a row, then we have trouble resyncing. My feeling is that you need a new ISP at that point. Also, there are very few applications that deal well with losing 2 to the 32 packets in a row. Anyway, I don't think that's a realistic concern. We made provisions to accommodate multicast for multicast SAs in our demultiplexing process. We took the default algorithms, moved them up to a separate RFC to make these more modular documents, and we added some new features that maybe nobody will ever use. They are traffic flow confidentiality features. So if you're trying to hide the nature of the traffic between 2 points, you can do that in a fairly efficient fashion based on these new facilities. We also revised the IPsec architecture to put in place a new processing model. That model clarifies a lot of things and allows for very high-speed implementations. And we did something that was an embarrassment the first time around because we had one set of people working on the key management protocol and one set of people working on the rest of the architecture, and we were all very busy. In the first version of this, there were things described in the SPD that Ike couldn't negotiate, which was a pity. So we fixed it the next time around, mostly by making Ike more flexible, and so that there is a one-to-one correspondence the way one would hope. I won't go through decorrelation today. Let me just skip to the new processing models. This is what the new model looks like outbound. Basically, traffic heading out, the first thing you do is select the right SPD. Why might you have more than one? Well, remember the PPVPN people. If they have a device serving a lot of customers, each customer really has its own SPD, so you have to select the correct one. Then we have figured out how to do caching here, and that's through decorrelation, and that's nice because the crypto algorithms can be very, very fast in hardware. And so you ran the risk that the lookup, a linear lookup in a security policy database, just like a linear lookup in a firewall filtering rule set, could be the slow part of the process, and we wanted to remove that as a potential obstacle. So decorrelation lets us do that so we can have a cache for the SPD. If you find the entry in the cache, you go ahead, you apply AH or ESP appropriately, or discard the traffic, or bypass it. And then the forwarding module is explicitly called out because if people wanted to do nested applications of security associations, that's one of the things you'd have to be able to do there. The other direction is a little more complicated, inbound processing. If it looks like IPsec traffic, we shuttle it off to one side, process it, and then do the check in the Security Association database to make sure from an access control perspective that the traffic that has just arrived is what should be arriving on that security association. If it doesn't look like IPsec, well, we shuttle it off to one side if it looks like it's ICMP traffic, because this is unauthenticated ICMP traffic, and that's potentially dangerous, and we have rules about what you should do with that. And if it's not IPsec and if it's not ICMP, well, then presumably it's trying to bypass, and we check to see if it can be bypassed or whether it's going to be discarded. And again, there's a forwarding loop here going through a cache of the SPD in order to accommodate some fancy things that you might need to do. So we have just one standard for security in the IETF at the IP layer. And that's what we've been talking about, IPsec. We have other choices of how to provide security. We have security up at the session layer, which is slightly embarrassing because the TCP IP model didn't have a session layer until SSL came along. We have people producing what I refer to as virtually private networks at layer 2 and layer 3, where we use no cryptography and we assume that gentlemen will not look at other people's traffic. We rely on operators to set a bunch of bits correctly in switches. This is not my idea of a great way to do security, but we do have ways of doing that. But from a cryptographic standpoint, this is the one way that we do it in the IETF at the IP layer. We architected from the beginning the notion that the peers in this might either be hosts, which in principle works fine but is almost never used in practice, frankly, or intermediate systems that we label security gateways. And in fact, what we see today, the two primary uses are in fact host to security gateway for road warriors and security gateway to security gateway for VPNs in an enterprise environment. Every modern OS ships with this. So we've succeeded in that regard, that it's been integrated into the operating systems, and everybody who's worked on this feels very good in that regard. Most of these, of course, are not supporting the RFCs I've just been talking about, the 4301, 2, 3, 4, et cetera series. They're still doing the older series, 2401, 2, et cetera. It is not just encryption. Access control is an essential part of this. This is very different from TLS. When I hear people talk about TLS VPNs, not only is that much more restrictive, because TLS or SSL, as currently defined and deployed, especially for SSL, works only on top of TCP, and therefore I wouldn't really want to be running VoIP over it, for example. But it doesn't do access control at all. In fact, here's a little question-answer game you can play with your friends. TLS and SSL are very widely used. You connect to websites. You get a certificate from the website, verified, etc. Which part of the spec talks about how you process certificates? Answer is none. TLS and SSL only describe the carriage of certificates. They don't say anything about processing them nothing whatsoever. It wasn't until Eric Rescorla wrote an informational document on HTTPS as a definition that ever appeared in any standard fashion. It was just what Netscape wrote and Microsoft later copied. That's what defined it. And I'm never comfortable with that approach. As I said, it's not just encryption. It is a communication access control mechanism. And there are other applications now looking to make use of it. So there's a recently approved document will be published as an RFC for OSPF version 3, making use of it with a lot of trouble because they need to do some multicast stuff, and we don't support multicast as well as we'd like to. BGP, it's being debated now in the IETF whether we should update the TCP MD5 checksum hack or whether we should move to use IPsec instead. And we have a new working group, Buttons, Better Than Nothing Security. You just can't make this stuff up. People have to propose it, which is unauthenticated. IPsec in hopes that, hey, maybe more people would use it if they didn't have to have that pesky authentication infrastructure in place. We'll see how that works. So, since we don't really have time for questions, but I have a tradition of always ending with a bird photography slide. Since I do bird photography, I had to put one of those up.
Okay.
Thank you.
Actually, we do have time for a couple of questions because we started 5 minutes late, and I'm going to propose that we go 5 minutes into lunch hour anyway. So if we have a couple of questions, I've seen two hands, but the microphone's gone there. Next microphone could come down here.
Hi, my name is Jean-Marc Cuzet from Juniper Networks. I would like to ask you your view about one thought. Today, the security model is based on many systems in the network that do deep inspection of packets up to layer 7. And the IPv6 evangelizer promote a lot the IPsec usage for end-to-end security between hosts, right? So that means that all these devices will not see anything in the packet anymore, right? Which means that we rely on intelligence in the host to do all the security job, like deep inspection, virus detection, etc., in the host itself. Because if it passed the host barrier, then we have a highway, which is the IPsec, that goes through directly to the next host, right? So it seems to me that there is two huge impact of this. One is in the security industry, which will be impacted a lot, and also on the operational model, because today, if you take a university or campus, they build their security model based on system they acquire, they understand how to use it, they have people to manage them, and they don't have much control on the hosts. You know that is in this community, many people use different systems, different software. Sometimes the researcher want to have a different system than the next one. So this is also going to have an important impact to the operational model. So I would like to ask you your view about this impact to both industry and operational model.
Sure. The observations you made certainly are ones that people have made before. And that's why I said that the way we see IPsec being used almost exclusively today are in two of the three possible cases. We're not seeing host-to-host use of IPsec. We see host to security gateway and security gateway to security gateway, and that in large part is motivated by just the observations you made. That is, the people who are responsible for enterprise security want to do packet inspection as a service to their set of subscribers, and so they want to terminate the security association at a point where they can still do that. And that's the primary reason that happens. So architecturally, we're capable of doing all three kinds of connectivity, but in practice, mostly what we see is the host to gateway or gateway to gateway, so it doesn't interfere with the way people have deployed intrusion detection systems, antivirus systems, things of that sort. The folks in the buttons working group, I think, would like to promote more host-to-host use of it, and I think that's ignoring the real issues that you mentioned.
Yes.
So we can't have it both ways. That kind of inspection is passive wiretapping, and we're here to prevent that. So it's really something that people get to decide as they deploy it. But architecturally, we can accommodate all of those, and it's up to the people who are making the deployment decisions to decide how to turn it on. And a compliant implementation can work in all of those cases. So I think we're okay in that regard.
Okay. I think it's a real opportunity here to clarify this and have people, really studying this new security model, because in many places where we evangelize IPv6, we don't talk about this at all, and I think this is a major, not issue, there is a major, real opportunity to explain things and think about new models. Yeah.
Okay.
Thanks.
Thank you.
Okay, over here, please.
Janos Macsi from Hungary. I have, more exactly, I have two questions. One question regarding how important do you think the IPsec is, how IPsec is important for IPv6 deployment? Because sometimes I see IPv6 presentation that, okay, IPv6 provides everything, every kind of security problems with IPsec. So I don't think that is a solution for every kind of problem. And the other question is regarding the scalability of the IKE. Can you comment the scalability of the IKE protocol in a real-world environment, host-to-host communication? Whether it's possible, do you think it's possible to deploy host-to-host IKE setup, or how do you feel that field?
Okay. With regard to the first question, yeah, it's unfair to say that IPv6 with IPsec solves all security problems. It solves a certain well-defined set of security problems, and because IPsec is already available with IPv4, it doesn't provide the strong motivation for transitioning to IPv6. So, long ago when we were looking at the transition from 4 to 6 in the IAB, we looked at what things we felt were deficiencies in version 4 that would be addressed in version 6 that would motivate people to make the switch, and that hasn't worked out as expected because things like IPsec were designed to work in both environments. Only v6 would mandate it, but everybody now has it in v4. So, but you're absolutely right. It is not a panacea. There are certain things that it does and hopefully does well, but that's it. With regard to IKE scalability, I'm not sure exactly what concerns one would have there. IKE itself has no trouble being used on a host-to-host basis. The reason it's not used on a host-to-host basis, typically, are the things that the previous questioner mentioned, which is the people running firewalls don't want to see protected traffic going through there that they can't examine. And the second part is, what's the basis for doing the authentication, the sort of thing that Mike mentioned in his talk this morning? What's the basis for people doing authentication on a peer-to-peer basis? Most of us don't do that. We do authentication as users to a server, but we don't do it on a peer-to-peer basis. So if you have any authentication infrastructure that works in that latter kind of model, then I can make use of it. I can make use of passwords. We call them pre-shared secrets, but they're just passwords, really. They can be big. It can make use of public key infrastructure, but we don't have a universally deployed public key infrastructure that everybody subscribes to. So it's not IKE per se that I think has any problem scaling to deal with host-to-host level stuff. It's really the authentication infrastructure that comes up. And if you believe in the work of the Buttons Working Group, we don't need no stinking authentication infrastructure. We just won't know who we're talking to. So. Okay, thank you.
Okay, thank you very much. I think we probably won't have any more questions now, but I'm sure you can call us Steve at the lunch hour, or if Mike's talk is unbelievably short, which I'm sure it won't be because he's got lots of good things to say, we might have time at the end. So it gives me great pleasure now to introduce Mike Warfield. Now, you've heard from Steve the theory or the specification from the standards perspective. We're now going to hear about IPv6 from the coalface, from a practitioner, and what the security implications of IPv6 are, from someone who's one of the all-time original, shall we say, hackers. He's been a security expert for 30 years. He's been a Unix expert for 20 years. And who better then could we have to say what are the real implications from the coalface of IPv6? Thank you, Mike.
Okay, thank you.
On? Oh, cool. Welcome.
We don't have the pictures. Just do a function F7 or something.
It should have. Yes, no? We can pull it up on this one real quick then. Possibly. It usually comes up right away. No, no. No, not switching on the cover switch either. Oops.
There's something gone wrong with the internet connection as well. I've got no internet connection. So
Oh, yeah.
put it on the stick. Just put it on the stick, Mike. There's no internet connection at the moment, so we don't have. We can't go through the site and download it.
He's just moving it on.
Okay. There you go. Put it in full screen mode there. Let's
Sorry about that.
no problem. Let's see USB. Whoop. See if I can plug this in and see what happens.
I didn't copy it, Mike.
Oh,
I didn't copy it.
all right.
Let
Just
me-
going to try and.
Do you want me to copy it?
Oh, you can do it either way now. I just wanted to get my little toy plugged in here.
Okay. Go back to it. Right.
All right, cool. Is that working or not? Nope. Oh well. Yeah, don't you just love it when you're coming up on a security talk and somebody says, "Plug that in and let's see what happens." Trusting. Okay, I guess I'm going to have to do this. Oh, it worked. It just.
Slow.
Previous. Okay, at least I know I can go forward. Okay, so, welcome. I come before you today with good news, and I come before you today with bad news. We've just heard some of the security features in IPv6, and the good news is that IPv6 is becoming quite popular in certain segments of Internet society, and this has some interesting implications for our network security. The bad news is that it's becoming very popular in certain segments of network society, and this has some very interesting implications for our security. So that's what I'm going to talk about today. Not so much the security features, which I'll touch a little bit on that, but I'm going to talk about the security implications of IPv6, and not just for IPv6, but also the security implications of IPv6 for our IPv4 networks. And at one time I was tempted to say for IPv4 only networks, but I'll be honest with you here. For the last 4 years, I have searched for an IPv4 only network, and I have utterly failed. I have yet to find a single IPv4 only network. Now, IPv6 does support a number of interesting features. Expanded addressing, formalized address boundaries, IPsec as we've just heard, quality of service, stateless and stateful auto configuration, dynamic renumbering, transition tunnels, robust resistance to brute force scanning, and it has no broadcast address. All of these things have implications toward our security. They have an impact on our security. IPv6 also represents a paradigm shift, a change in the way this is modeled. It's not merely IPv4 with fat addresses. You talk to a lot of people, it's like, well, we just got big addresses. No. IPv6 changes from a paradigm of scarcity, where we have to be efficient in our allocations, to a paradigm of plenty, where we have lots of addresses with which to work with. Some people say, well, why do we need 16 billion addresses in a subnet? Well, the answer is we don't need that many addresses, but we can use that much address space, and we can use it quite effectively. So even if IPv4 were even if IPv6 were just IPv4 with fat addresses, which it's not, it couldn't be because of this paradigm shift. IPv6 code stability, IPv6 has been around for many years, but it's still under development. There's still a lot of development going on. There will be new bugs that don't exist in IPv4, but there is a lot of code shared between them. But few vulnerabilities derive exclusively from the IP layer. Few exploits, few holes derive solely from the IP layer. Lessons learned in IPv4 development have also improved our ability to develop IPv6, but there will be instances where things come up. OpenBSD had a bug in their IPv6 stack that allowed the kernel to be crashed. Microsoft Windows here a little while ago reinvented an old wheel in that they introduced the land attack, which is, if you go way back almost 10 years, there was this bug in Solaris where if you set certain ports and addresses the same, you'd blow up the stack. Well, Windows reintroduced the land attack only on IPv6. So we will still have some of these things. Just as a few numerical guesstimates, if you look at IPv4, IPv4 has 4 billion host addresses. That goes 0.0.0.0 to 255.255.255.255. Just as some pure guesswork, and I'll have to get a little closer to my notes here. If all of IPv4 were divided up into /24 networks, you'd have about 16 million networks. If all the allocated space were /24s, you maybe have 4 to 8. Some of these host addresses have got NATs. An estimate of broadband and DSL accounts, maybe 20 million of these. Some of these have NATs, some don't. Some have networks behind them, some don't. I typically say my best wild guess. You might have 4 million to 20 million routable networks, probably less. If you look in the core IPv4 routes from BGP, and that's just from last month, you'll find 181,000 routes, and routing in them, you'll find 1.51 billion routable host addresses, unicast addresses. Some current IPv6 estimates. The IANA gave up on handing out little sub-TLA assignments. They're now handing out huge blocks of addresses to the regional registries. And you can check on what the current state of this is. It's really been exploding the last 12 months. Global core routes in BGP for IPv6 last month was 640 routes is all. Not counting 6-bone traffic, not counting 6-to-4 traffic, not counting Teredo routing, and I'll get into what a Teredo is. Routable IPv6/48 networks in the core, 1.65 billion. There's more IPv6 routable networks in the core gateways right now, and have been for almost a year now, more routable IPv6 networks in the core gateways than there are routable IPv4 addresses. IPv6 supports a number of interesting transition mechanisms and things that we should pay close attention to. These are intended to promote IPv6 adoption and interoperability, compatibility addresses in IPv4, aid IPv4 to IPv6 communications. We have things like SIT, or 6-in tunnel, 6-in-4, 6/4, 6-to-4 auto tunnels, IPv6 in UDP and various encapsulations, proxy servers and services and protocol bouncers. There's all kinds of different ways to get IPv6 and IPv4 communicating and to smoothly transition into this. 6-in-4 is the simple internet transition, 6-in, popularly referred to as 6-in tunnel, protocol 41 in IPv4. This is the basis for several of the tunneling mechanisms, several tunneling schemes. You can have static tunnels, or you can even have automatically configured tunnels, the 624 tunnels. It can pass over many of the IPv4 NAT devices, but not all, and it's not very reliable. Most of the tunnel brokers will provide IPv6 using SIT tunnels at the very least. It's kind of the lowest common denominator for many of them. 6-to-4 auto tunnels using a little address magic. Each and every IPv4 host address has an entire IPv6 network of 65,000 subnets at 16 billion host addresses each assigned to that one IPv4 address. And you don't need any tunnel broker for that network. You don't need to ask any permission for that network. You don't need any kind of static configuration for that network. Teredo, I mentioned Teredo earlier. Teredo I like to single out because to me Teredo is proof positive that the IETF has a sense of humor. Teredo is IPv6 over UDP. Well, the previous draft of Teredo was also called shipworm. And Teredo is a species of shipworm. It's a mollusk that bores holes in the wooden hulls of boats and docks and piers and rots them from the inside out. So you can imagine what they were thinking of when they defined this standard of IPv6 over UDP and what it does to your security parameters. Teredo has some very interesting features, including a they say a robust variation on the STUN protocol, another lovely acronym that comes out of the IETF. Stands for Simple Transition of UDP over NAT. Basically, with STUN, you can have two clients sitting behind NAT devices communicating with a STUN server or a Teredo server, and the Teredo server is just there as a negotiator, and he will tell these two devices, both behind NATs, how to talk to each other. He carries none of the production traffic. He merely tells them how to start up a communication peer-to-peer behind two NAT devices, and does it quite effectively. Teredo servers, so as I say, Teredo servers carry no production traffic. They merely set up how the clients communicate. The relays are used to communicate between the other top-level address spaces and the Teredo clients. And Teredo relays are currently advertised in BGP. So I quite often, from here, I've used Teredo to talk with the rest of IPv6. And works very well. There's a project that provides Teredo on Linux and FreeBSD and other operating systems. It's called the Merito project. It's built into Windows XP and will be in Vista as well. At one time, Windows XP, as soon as you turned on IPv6, it turned on configured Teredo service and communicated with one of Microsoft's Teredo servers. We have detected IPv6 Teredo traffic in corporate networks. So people are turning this on, whether they know it or not. It used to use a 6-phone address. The IANA has recently assigned it to address prefix 2001:0/32. And it is now an IETF standard RFC 4380. There are other IPv6 over UDP transports. They basically have much the same effect on firewalls. They just don't even see them. They blow right past them. You have, let's see, TSP, Tunnel Setup Protocol. This is one that's promoted by the Freenet 6 project out of Canada. TSP is also used for the DSTM transition mechanism. TSP is still in an ETF draft. We also have AICCU, which is an automatic IPv6 connectivity client utility that's promoted by 6XS here in Europe. And then we also have OpenVPN, which at one point was being used by the German Join project as a tunnel broker service. And again, this works over UDP, different UDP different UDP port numbers. We have other methods of transporting IPv6 as well. It can be basically IPv6 can be transported over anything that can transport IPv4. You can transport it over PPP, either native or tunneled IPv4, and using 6N4. It can be transported over IPsec, IPsec NAT-T. So now you have Torito in that you have it over UDP in the form of NAT-T, but you also have it encrypted. 6/4 uses IPv4 multicast. ISATAP, now there's a complex setup using 6N4 for large enterprises. I haven't really got much experience with that, but you can also use the generic routing encapsulation protocol 47, where you can tunnel 6/4 or 4/6 or however you want. We also have the transports of ill repute. These are some of my favorite ones. Ping tunnel. When you really need to check that email and you need to get through that wireless access point that he's got the security set up on, ping tunnel. Tunneling over ICMP echo and ICMP reply. We've also got TCP tunnel, H tunnel, tunneling over HTTP. The Swiss Army knife of these is the covert channel tunneling tool. It brings together a number of covert channel tunnels, which you can transport all of this over. The transports are interesting, but they're transporting IPv6 in this case, which transports that routability and that global addressability into your networks. And yes, these things are in use. The Internet Underground is already active on IPv6. They've got IPv6 only IRC channels. They've got IPv6 only FTP sites. They've got IPv6 only websites. The most notable thing about IPv6 right now, and I don't see my friend who told me about this a couple of weeks ago, but he says the chatter in the underground about IPv6 has actually died down. And the reason for it dying down is not because it's not popular, but it's because it's ubiquitous. It's no longer news. It's not just the elite are on IPv6. They've all got IPv6, and they can use IPv6 against you. They have the expertise. Interesting thing. And I should have mentioned when I get to this slide. Normally, when you pick up a good book on IPv6, there'll be a chapter in it on security, and quite often the main focus on it will be what we just heard from my esteemed colleague about IPsec, as if that's the only thing to do with security. IPsec is extremely important, but there are more aspects to it. I was pleasantly surprised to pick up this book out front yesterday and paw through it and the security chapter in it. And I wonder if they've sat through one of my talks, because they've got a lot of the same points that I make in this talk. And things like the end unit identifier. One of the biggest threats to IPv6 is bringing the IPv4 mindthink to things like the host field, this lower 64 bits of the address, the end unit identifier. I've seen people assign them out. 1, 2, 3, 4, 5. It's like, okay, we really don't need to be doing that. And then we also have EUI 64, which takes the MAC address and kind of munges it around and plugs it into an address, and now you've got a great big address that auto-configures statelessly. What's interesting is if you looked on one of my servers right now and went through the WTemp records, you would see a certain lower 64 bits constantly throughout this. But the upper 64 bits would be varying. And so you could tell when I was at my desk at my office, when I was at home, when I'm here at a show, where I'm at is showing up. You know it's me because the lower 64 bits are the same as that laptop right there. But the upper bits are telling you where I'm wandering around and what I'm, not what I'm doing, but you can tell a lot about what I've been doing. Well, that upset a few people, that caused some concerns, and they brought those concerns to the IETF, and so they came up with privacy-enhanced addresses. These are addresses that are generated at random. Each time you boot up, you have a different lower 64 bits. Periodically, those addresses can change while you're running. It will add a new address, and as soon as you're done using all your connections and everything, all your references to the old address are gone, the old deprecated address disappears. So your machine can change addressing over a period of time, or even at random, it can change addresses. Now, think about that in terms of security, and you're trying to track down that virus-ridden, spam-propagating critter on one of your networks, and it keeps changing the address on you. You can also use cryptographic client addresses. I've seen proposals where people will actually use the client address through a cryptographic algorithm, and then the server basically locks based on what that connecting address is. And I've even set up some cases where I'll put SSH on a set of addresses that change periodically on a server. But I just keep updating DNS using T-SIG signed records, and I can find that service looking it up in DNS. But it's really tough to find when it's hopping around in an address field, especially an address field as big as that. So we do have some problems with EUI, such as well-known EUI addresses. A good example is in how the defaults are set up for 6-4, which is the 2002 top-level aggregation address. In Linux, the default is 2002, followed by your IPv4 address, ::1. The EUI, in this case, is 1. Windows is 2002, IPv4, ::IPv4. Okay, they both chose differently, and they both chose poorly. Both of these are scannable. I can scan for those addresses just as easily as I can scan through the IPv4 address space. What's even better is when I do so, I can tell the difference between a Windows box and a Linux box. It's given me more information than what I had before, although it's not hard to find out once you've found the box. Teredo host addresses are predictable. They're based on the IPv4 address of the server and on the client. But some of these trivial addresses are useful as dummy addresses and client addresses. I've seen cases where router defaults are using trivial EUI addresses. Sometimes people want to put simple addresses for their DNS servers. They save a few bytes and type, a few keystrokes in typing. But we really don't need to quite be that bad about things. And you can make even the SLA, the subnet field, you can use router policy type addresses. You don't need to use simple route subnet numbers. Connecting with some of my buddies on IRC, the Samba team, first one of my Samba team members sent me a message saying, okay, one, this is not my address is bigger than your address contest. But his second question was he saw my address and he just, 8200? Question mark. Okay, well, first off, he knew what he was looking at in an IPv6 address. He looked at my SLA and said, what in the world have you got a subnet number that high? Well, the high order bit was the difference between office and home. And the next one was the next subnet in at home. So there were reasons for having this, not just numbering it straight through. Oops, wrong way. Now I've mentioned stateless auto configuration. This allows for auto configuration of IPv6 addresses, gives you dynamic renumbering of your prefixes. Your subnets can have multiple parameter routers with different prefixes, different lifetimes, and different preferences. Interfaces can have multiple global addresses and EUIs, but that also means that rogue routers can inject IPv6 routes on your IPv4 address nets and may interfere with your IPv6 routers. This is sort of like our cache poisoning on steroids. And accidents do happen. You do occasionally get accidental router advertisements. I still haven't laid my hands on the guy in IT that accidentally bridged 2 of my subnets one day, and so the router advertisements got crossed, which screwed them both up. And I had to then force router advertisements out on both networks that lied, said they were the other, but set short lifetimes in order to get the router advertisements to expire. So you can't have little random acts of terrorism just based on how these things should be working. And that was tough to track down, too. I could not figure out why in the world my outbound connections worked, but my inbound connections did not work. And it's like, or one or the other. Scanning IPv6, IPv6 should be 4 billion times harder to scan a single subnet than all of IPv4 end to end. Efficient, dense allocations, however, such as doing things incrementally, that equals feature-rich targets. If you can predict where the addresses are, then it becomes easier to scan. It's easy for us to screw it up. It's got an inherent robust resistance to scanning, but we can certainly make it worse. Sparse allocations make brute force scanning impractical. Now, there are some optimizations. If you're using EUI 64, well, then you kind of reduce the search set. So this is, it's not scan proof, but it is resistant to scanning. And worms are not going to be able to just arbitrarily brute force scan around. But I suspect we will still have people poking at the .1 address thinking that, oh, there's lots of people who came out of the IPv4 world and they're going to want to put on all their routers on .1. I can almost guarantee you that's going to happen. V6 and broadcast. No broadcast addresses are in IPv6. All of the broadcast functionality has been subsumed into the multicast addresses. Every time I mention this to people I know in the network business, they say, but if you don't have a broadcast address, how do you do? And then they stop. They realize there's nothing that you need a broadcast address for that can't be done better with these multicast addresses. But without, there's no local broadcast. There's no, let's see, no directed broadcast. You can't send a packet into a network that's a directed broadcast, and there's no global broadcast address. So no more Smurf amplifiers. Bye-bye. No more broadcast scanning for nodes. No more directed broadcast food fights. Now, I don't know if you know what that is, but that's a neat little trick. Fortunately, we've managed to quash most of these, but the trick used to be that you would send in a directed UDP packet into an IPv4 network addressed to the CareGen port. And you'd spoof it from the broadcast address of that to the echo port. So you can imagine why it's called a food fight. But this doesn't help much with local broadcast DDoS zombies that could still hit the all nodes network on the local subnet. So it's not a cure-all. It helps. It just eliminates a few problems. Let's see. Now, a lot of things, again, these aren't cure-alls. And a lot of people say, well, isn't a lot of this just security through obscurity? You're just hiding behind big addresses and such. You're hiding by not allowing broadcast. You're hiding behind privacy addresses. You're just hiding. No, it's not really. Systems are not hidden. You can still look them up in DNS, and they connect just fine and still be sniffed just fine, unfortunately. Systems merely can't be scanned for by brute force. You've taken away a hacking tool. You've taken away a worm propagation vector. You've removed a DDoS tool, the Smurf. You've made life harder on spammers. They can't scan for open relays. And you've made life harder in hacker war participants, what my friend Rob Thomas likes to refer to as shelling matches, where the hackers are attacking and beating up on each other and trying to steal each other's zombies. Looking at IPv6 and the anatomy of a hack. We typically, in anatomy of a hack, we talk about identifying targets, gaining access to your targets, acquiring shell, elevating privilege, cleaning up your traces, and securing communications and future access. IPv6 impacts some of them, but not all layers on this model. And sometimes it favors the attacker, sometimes it favors the defender. Identifying targets, brute force scanning, is impractical. Targets have to be individually chosen through some other method, either, and if you block DNS transfers, then you can cut down on their ability to enumerate your host, but they can still look up www and attack it. Port probes are still possible once you've identified a system. Security access, you can put your security access on different addresses. So you don't have to have SSH on your www address. You can have SSH on some other address that you access through some other method. So in this particular case, the advantage tends to be in your favor. It tends to be in the favor of the defender. Gaining access to other systems may be acquired from compromised systems secured by IPv6 tunnels. Once he's on there and established a tunnel, then he can start to use that to attack other systems with a little more ease. Multiple systems can be accessed and routed out through a single host anchoring IPv6 tunnels. Additional global routing may contribute to accessing systems behind firewalls or on private IPv4 space. It doesn't care. IPv6 routing is independent and orthogonal to IPv4.